Welcome to the Curious Voyager. It's lovely to have you here tonight, wherever you are. Maybe you're under a heavy blanket with just one lamp still glowing in the corner. Maybe you're on a train, watching the dark slide by the window. Maybe it's late and the house has gone quiet around you, and this small voice is the last thing awake with you. Wherever you are, settle in. Let your shoulders drop. There's nowhere to be and nothing to solve. Before we begin, let me ask you something, the way I always do. Where in the world are you listening from tonight? What time is it in your corner of the dark? I love picturing all of you out there scattered across so many time zones, all drifting toward the same quiet. And if you enjoy these slow journeys and want more of them, a gentle like and subscribe really does help this sleepy little channel keep going. To those of you already here, already part of this, thank you. Truly, small creators like me rely on your kindness more than you know. Now, here's my promise to you, the same one every night. We're going to move slowly, softly, one small idea at a time, with no rush and no pressure. You don't have to understand every piece of this. You don't have to follow it all the way to the end. In fact, if you drift off somewhere in the middle, if your eyes get heavy and the words begin to blur into something warm and far away, that's perfectly fine. That's the whole point. The ideas will still be here when you wake. They're patient. They've waited a very long time already, as you'll see. And I'll try not to make any of this so interesting that it keeps you awake. But if it does, well, at least you'll have learned something lovely. A fair trade, I think. So let's begin, shall we? I want you to imagine something with me. Hold it gently in your mind, the way you'd hold a warm cup you don't really need to drink. Imagine an object sitting in front of you on a table. It's a crystal, solid, real. It has edges and a shape and a weight. If you tapped it with a fingernail, it would make a small, clean sound the way a glass does. It is, in every way you can see, a solid thing. It holds its form. It doesn't sag or slump or run. You could set it on a shelf and come back in 100 years, and it would still be sitting there holding the same shape, perfectly still. And yet, this particular crystal can flow, not melt, flow. Some part of it can move through itself, glide through its own structure, like water finding its way through sand, except with no resistance at all, no friction, no drag, no slowing down, ever. A current could start moving inside this solid thing and simply never stop. Not for a minute, not for a year, not for 1,000 years. It would just keep going, silent and frictionless, through a thing that is, at the very same instant, as rigid and ordered as ice. A crystal you could, in a sense, pour through itself, solid and flowing. At the same moment, both, fully, with no contradiction. If something in you just quietly bristled at that, if a small voice said that can't be right, those are opposites, then you're in exactly the right place. Because for a very long time, the best minds in physics agreed with that small voice. They said it plainly. A thing cannot be a rigid solid and a frictionless flowing liquid at the same time. Those two natures cancel each other out. You get one or the other, never both. And they were wrong. Or rather, they were missing something. And tonight we're going to drift slowly and softly through the long, strange, patient story of how they found out. It's a story that begins with a prediction made in 1969, decades before some of the people who'd finally confirm it were even born. It passes through a famous discovery in 2004 that was celebrated, then quietly came apart in scientists' hands like wet paper. And it ends, or, well, it arrives, for now, at something that happened just recently in 2025 that is so strange I still find it hard to say out loud without smiling. Scientists took light, the most weightless, the most ungraspable thing we know, the thing that can't be held, can't be stacked, can't be set down on a table, and they made it hold the shape of a solid. But I'm getting ahead of myself. We have all night, and I promised we'd go slowly. So let's go back gently to that first knot in the rope. The thing that sounds impossible. Let's untie it carefully, because once you see how it comes apart, the whole rest of the story becomes calm and clear, and you can let it carry you wherever you're going tonight. Here is the heart of it, and it's softer than it sounds. The trouble is the words solid and liquid feel like opposites because of how we use them in everyday life. Ice and water, brick and milk, hard and runny. We treat them as two ends of a single line, and a thing slides from one to the other when it melts or freezes. So of course something can't be both. It would be like saying a place is both north and south of you at once. But that everyday picture quietly mixes up two completely different ideas. And when you pull them apart, gently, the way you'd separate two pages stuck together, the impossibility just melts away. Think about what solid really means, deep down. Underneath the hardness and the holding its shape, what makes a crystal is order, arrangement. In a crystal, the atoms aren't scattered around randomly like a crowd milling about a square. They're lined up, stacked in a neat, repeating pattern, row after row after row, like oranges in a market stall, or like the tiles on a bathroom floor, going on and on in the same rhythm. That repeating, orderly arrangement is what crystalline really means. It's a pattern in space. Every atom has its assigned spot in the lattice, and it stays there. So when we say solid, what we really mean at the deepest level is ordered, arranged, rigid in its pattern. Now think about what liquid really means, or rather, the special slippery thing we actually care about here, which is flow, frictionless flow, the ability to move without resistance. In an ordinary liquid, like the tea cooling beside you or the water in a glass, things flow, yes, but they flow with friction. There's drag. Stir your tea and it swirls, and then slowly it stops. The motion bleeds away into warmth and stillness. That bleeding away is friction, viscosity, the liquid resisting its own movement. But frictionless flow is a different and far rarer thing. It means motion that never bleeds away. Stir it, and it just keeps going forever, because nothing is there to slow it down. Do you see what's happened? We've taken the one big idea, solid versus liquid, and we've quietly split it into two completely separate questions. One question is about arrangement. Are the atoms in an orderly, fixed pattern in space, or are they jumbled and free to wander? The other question is about flow. Can things move through this stuff without any friction at all, or not? And here's the gentle, beautiful part. Those are two different questions. They don't have to give the same answer. There's no law saying that a thing with an orderly arrangement must also have friction. Those are separate properties of the world. So you can, in principle, have something that is ordered in its arrangement, a true crystal, rigid, patterned, holding its shape, and that also lets some part of itself flow through that arrangement with no friction whatsoever, ordered in space. Frictionless in flow, both true at once. Not a contradiction at all once you stop letting the everyday words bully you. Just two different properties quietly coexisting in a single, strange and wonderful kind of matter. That kind of matter has a name. A simple, almost storybook name. It's called a supersolid, a super solid. Solid because it has that rigid, crystalline order. And super, borrowed from its cousin, the superfluid, because of that frictionless, never-stopping flow. A supersolid is a state of matter that has both at the same time the rigid, repeating, periodic order of a crystal and the zero friction, zero resistance flow of a superfluid, two natures that physics long thought could not share a single body living together gently in one. Let that settle for a moment. There's no need to grip it tightly. Just let the shape of it rest in your mind. Order and flow. Rigid and frictionless. A crystal that pours. Now, if you want the deeper, truer way scientists say all this down, and you don't need it to follow the story, so feel free to let this part wash over you like a lullaby, it comes down to a lovely phrase: the breaking of symmetries. Two symmetries broken at once. That's the rigorous definition of a supersolid, and it's the same idea we just walked through, only dressed in its more formal clothes. Here's what that means, slowly. A symmetry in physics is a kind of sameness, a way the world looks identical no matter how you shift it. Imagine a perfectly smooth, featureless plane stretching out in every direction, with nothing on it, no trees, no hills, no markers. If you took a step in any direction, the plane would look exactly the same. There's no special spot, no preferred place. That perfect sameness, that it looks the same wherever you stand, is a symmetry. Specifically, it's called translational symmetry, onto the freedom to slide or translate your position anywhere and have nothing change. A liquid, before it freezes, has that symmetry. The atoms are everywhere and nowhere in particular, smooth and uniform like that empty plane. Slide your viewpoint a little to the left, and the liquid looks just the same. But when a crystal forms, when the atoms snap into their neat, repeating rows, as that perfect sameness breaks, suddenly there are special places right on an atom or in the gap between atoms. The plane has sprouted a regular grid of fence posts. Now it matters where you stand. Slide your viewpoint a tiny bit, and you've moved off a fence post and into a gap. The endless sameness is gone, replaced by a repeating pattern. Physicists say the translational symmetry has been spontaneously broken, and that broken symmetry, that newly grown spatial pattern, is exactly what makes the thing a crystal. The crystal is the broken symmetry. That's the solid half of our supersolid. Then there's a second symmetry, and this one is harder to picture, so let it be a little fuzzy. It has to do with the strange, hidden, wave-like nature of matter when it gets very cold and very quantum. Down in that deep cold, a collection of particles can lose their separate identities and start to behave as a single shared wave, all marching in step, all sharing one rhythm. That shared rhythm has a kind of hidden dial to it. Physicists call it a phase. And in an ordinary uniform quantum state, that dial can be set anywhere and nothing observable changes. It's another kind of sameness, another symmetry, this one called U1 gauge symmetry or phase symmetry. You don't need the name. Just hold the feeling, a hidden dial that doesn't matter until suddenly it does. When a superfluid forms, when all those particles lock into one shared marching rhythm, that hidden phase dial picks a setting and the whole collection commits to it together. The freedom is gone. Everything is now in step. That second symmetry breaks too. And that broken symmetry, with that single, shared, committed quantum rhythm, is exactly what makes the thing flow without friction. Because there's no jostling, no disorder, no individual particles bumping and dragging against each other. They all move as one. That shared, locked-in rhythm is the super half, the frictionless half. So now you can hear the full, formal sentence, and it should land softly because you already understand it underneath the words. A supersolid is matter in which two continuous symmetries are spontaneously broken at the very same time. The translational symmetry breaks and you get the crystal. The the rigid, ordered arrangement. And the phase symmetry breaks, and you get the superfluid, the frictionless shared flow, both broken, both at once. In one body of matter, that's the rigorous both at the same time. Not a poetic flourish, a precise and demanding definition, and meeting both halves of it at once in real matter, in a real laboratory. That is the whole long hunt we're about to follow. But before we chase the supersolid, we should spend a little while with its gentler, older cousin, the plain superfluid, the one with only the flowing half and not yet the rigid one. Because to feel how astonishing a supersolid is, you first have to feel how astonishing it already is for anything to flow with no friction at all. And here, the story turns kind and a little funny and very cold. Let's go back, way back, to the 1930s, to liquid helium. Helium, you know it as the gas that fills birthday balloons, the one that makes your voice go squeaky, the lightest, most reluctant, most aloof of all the elements. Helium does not like to be anything but a gas. It clings to its gaseousness with extraordinary stubbornness. To turn it into a liquid, you have to chill it down to ferociously cold temperatures, within a few degrees of the coldest cold there is. And when you do, when you finally coax helium into a liquid, it just sits there in its little cold pool, looking, at first, like an ordinary, if very chilly, liquid, clear, faintly shimmering, quiet. And then you cool it just a little bit further. And it does something that when scientists first saw it genuinely did not make sense. There's a particular temperature. For helium-4, the common kind, it's about 2.17 Kelvin. Now, Kelvin is just a temperature scale that starts counting from the very bottom, from the coldest possible cold, which we'll talk about more later. For now, just know that 2.17 Kelvin is staggeringly cold, colder than the dark between the stars, colder than almost anything in the natural universe. And at that precise temperature, physicists call it the lambda point because of the shape of a certain curve on their graphs, like the Greek letter lambda. At that exact threshold, the liquid helium changes its nature entirely. It crosses over into a new state. It becomes a superfluid, and a superfluid does things that feel like gentle magic. The most famous one, and the one I love most, is this: a superfluid will climb. If you put some of this superfluid helium into a little open cup, and you set the cup down inside its cold chamber, the helium will not stay politely in the cup. A film of it, a layer so thin it's almost not there, just a few atoms thick, will creep silently up the inside wall of the cup, all on its own against gravity. It will reach the rim. It will flow up and over the lip of the cup like an impossibly patient tide, and then trickle down the outside, drop by drop, until the cup has quietly emptied itself onto the floor of the chamber. The helium escapes its container by climbing the walls. That thin, creeping layer even has a name. It's called the Rollin film, after the scientist who studied it. A liquid that climbs out of its own cup, all by itself, in the dark and the cold. There's something almost tender about it, I think. Something determined. And why does it climb? Because there's no friction to hold it back. In an ordinary liquid, the drag of the liquid against itself and against the walls keeps it pooled obediently at the bottom, but the superfluid has shed its friction completely. The faintest tug, and there's always a faint tug, a whisper of attraction between the helium and the surface it touches, is enough to pull it up and onward with nothing at all to resist. Zero viscosity. Viscosity is just the fancy word for that internal stickiness, that resistance to flow. Honey has high viscosity. It oozes. Water has less. It pours. And a superfluid has none. None at all. It's the smoothest, most slippery, most frictionless flow in all of nature. There's another trick it does, even stranger and even quieter. If you get a superfluid moving in a circle, say, set it gently rotating in a ring-shaped channel, it will keep going around and around and around, not for a while, not until it slows down. It doesn't slow down, there's nothing to slow it. The current just persists, circling silently, in principle forever. A persistent current, they call it, and that plain little name holds something almost unbelievable inside it. Motion that never, ever ends. Stir this cold liquid once, and it remembers that stir for eternity, turning quietly in the dark long after everyone has gone home and the lights are off. This is the frictionless flow. This is the super we were talking about. And it was discovered, this whole impossible, gentle world of climbing films and endless currents. Back in 1938, the credit goes to a handful of careful, cold-fingered scientists working at the very edge of what was possible. In the Soviet Union, there was Pyotr Kapitsa, a brilliant and stubborn experimentalist who pushed the helium to that lambda point and saw it shed its friction. And independently, at almost the very same time, working over in Cambridge, two others, John F. Allen and Don Misener, saw the same astonishing thing and reported it as well. Two groups in two different places arriving at the same impossible doorway in the same year. It happened in 1938, and it opened up a whole new wing of physics, the study of these superstates where matter, made cold enough and quiet enough, begins to behave as a single, shared, frictionless whole. Now I want you to hold on to the feeling of that, because everything that follows in our story grows out of it. Superfluidity, frictionless flow, the climbing film, the eternal current, is real. It's confirmed. It's been studied for the better part of a century. Scientists can make it, measure it, pour it, watch it climb. That half of our impossible crystal, the flowing half, was never really the mystery. We've understood frictionless flow for a long time. The mystery, the real ghost that scientists would chase for decade after decade, was the other half. The marriage. Could you take that frictionless flow and somehow lock it inside a rigid, ordered crystal? Could you have the climbing, endless, frictionless current of a superfluid living inside something that, at the same moment, held the stiff, patterned, repeating order of a solid? Could the eternal stir happen not in a pool of liquid, but woven right through the lattice of a frozen crystal? Flow threading itself through stillness? That was the dream. That was the supersolid. And it would turn out to be one of the most patient, most maddening, most quietly humbling hunts in all of modern physics. A chase after something that had been written down on paper as a possibility, as a daring idea, long before anyone had the faintest notion of how to actually find it. So let's drift forward now just a little from that cold helium of 1938 and into the late 1960s, when a few physicists sat down and asked a question that most of their colleagues thought was almost too strange to take seriously. They asked, what if a solid, a real, frozen, crystalline solid, could have a superfluid hiding inside it? What if the very stillness of a crystal could somehow be threaded through with frictionless flow? And the way they imagined it could happen is so strange and so beautiful that I want to give it room and tell it to you slowly, in the quiet that's gathering around you now. But first, just rest here a moment in what we've already found tonight. Two words that seemed like opposites, solid and liquid, gently pulled apart into two separate, peaceful questions. Order in one hand, frictionless flow in the other, and the slow, dawning realization that nothing, really, forbids a single thing from holding both. A crystal that pours, a stillness with an endless current running through it. The scientists who first dared to write that idea down didn't have the tools to find it. They only had the courage to say it might be there. And we'll meet them next with their daring 1969 idea and the curious clue, a kind of ghostly lightness in a spinning thing. They said would prove it if anyone could ever build a cold enough, careful enough, patient enough experiment to look. We'll follow that clue into the great helium laboratories and to a day in 2004 when the whole world of physics thought, at last, the ghost had been caught, but not yet. For now, just breathe. Let the cold helium climb its quiet walls in the back of your mind, endless and frictionless and unbothered by any of us. There's no rush at all. The crystal that flows has waited more than half a century to be found. It can certainly wait while you drift a little closer to sleep. Let me settle back then to the helium itself. Because before anyone could dream of a solid that flows, they first had to find a liquid that already did. And that liquid is one of the strangest things people have ever poured into a glass. Picture the year 1938. In a cold laboratory, two separate teams are working with helium. The second lightest element there is the same gas that fills birthday balloons and makes voices go high and silly. But this helium has been cooled, not a little, cooled until it gives up being a gas entirely and gathers into a clear, pale liquid, colder than almost anything in the natural world, and then cooled further still past a particular temperature, about 2 degrees above absolute zero, a point physicists came to call the lambda point, around 2.17 Kelvin. Let that number sit with you for a moment because it's hard to feel how cold it really is. Absolute zero is the bottom of everything, the coldest cold there can possibly be. 0 Kelvin, which is 273 degrees below zero on the Celsius scale. Nothing can be colder, and the lambda point is just barely above that floor, a whisper above the absolute end of cold. Colder than the dark between stars, colder than anything you have ever touched or ever will. And right there, at that whisper of warmth above the bottom of the world, the helium does something that should not be allowed. It stops resisting. In the warm world you and I move through, every liquid drags. Honey drags more, water drags less, but they all push back a little against anything that tries to flow through them or stir them around. That pushing back, that internal stickiness, has a name: viscosity. It's why a spoon slows in syrup. It's why a river eventually calms. Everything that flows against a little friction of its own, but this cold helium below the lambda point has zero viscosity. None. It is a superfluid. And that small word, zero, hides something almost impossible to hold in your head as you lie there. A superfluid flows with no friction at all. Stir it once, gently, into a slow circle, and it will keep turning and turning and turning. Not for a minute, not for an hour, but in principle, forever, with nothing to slow it down. Scientists call that a persistent current, a motion that simply does not stop because there is nothing left in the liquid to stop it. The two people credited with finding this, well, one of them was a man named Pyotr Kapitsa, working in the Soviet Union, and quite independently far away, two others, John Allen and Don Mizner, found the very same impossible thing at almost the very same time. They reported it in that same year, 1938. 3 people, separately, looking at the coldest liquid in the world and watching it refuse to behave. And here is the detail I love most, the one I want you to carry softly into sleep. A superfluid doesn't just flow without friction along the bottom of its container. It climbs. Imagine a small cup of this cold helium sitting inside a larger chamber. With an ordinary liquid, the cup keeps its liquid, of course. Gravity holds it down, the walls hold it in, and that's the end of the story. But a superfluid is not held by such ordinary rules. A vanishingly thin layer of it, thinner than you could ever see, just a film a few atoms deep, creeps up the inside wall of the cup all on its own. up and over the lip and down the outside with no pump, no push, no reason that the warm world would recognize. It simply flows where flowing should be impossible until the cup, given time, can quietly empty itself. The liquid walks up its own walls and leaves. That delicate climbing layer even has a name. The rollin film. A ghost of a thing, a few atoms thick, drifting upward against gravity in the dark and the cold, slow and silent and absolutely without friction. So picture it now, as you rest. A little cup of the coldest liquid there is and a thread of it whispering up the glass, over the edge, down the far side, gathering in a slow drip at the bottom of the chamber, while the helium turns somewhere in an endless circle that will never wind down. Nothing forces it, nothing stops it. It is simply what this matter is, this close to the bottom of cold. And if you've drifted part way already, that's perfectly fine. The helium will still be climbing its walls when you come back to it. None of this hurries. Stay with me if you can, though, because we're about to see why this strange, climbing, endless liquid matters so much for the crystal that flows. Here is the heart of it, said as plainly as I can. A superfluid is one half of our paradox already solved. It is the frictionless flow, the endless current, the part of the impossible pair that has the liquid's freedom. By 1938, the world knew beyond any doubt that matter could do this, that flow without friction was not a fantasy but a real thing you could chill into a glass and watch with your own eyes. The frictionless half was no longer in question. It was sitting there in the laboratory, climbing the walls. What was missing was the other half, the order, the rigid, patient, geometric stillness of a solid. Could you take this freely flowing thing and somehow give it a shape, a real crystalline arrangement, atoms or particles locked into a repeating pattern like the points of a frost flower on a winter window, and still let the frictionless flow run through it? Could you have the stillness and the current in the very same body of matter, in the very same instant? That, you see, is the deeper way to understand what we glimpsed at the start of tonight's journey. Physicists have a careful, beautiful way of talking about it, and I'll translate it gently as we go because there's no need to grasp every piece. When matter forms a crystal, when its particles settle into that repeating, orderly grid, they say it has broken what's called translational symmetry. It only means this: before the crystal, the stuff was the same everywhere, smooth and featureless, no special spots. After, it has chosen places, here a particle, there a gap, here there, in a fixed rhythm through space. The smooth sameness is broken into a pattern. That broken sameness is the crystal, that is order. And when matter becomes a superfluid, when it flows without friction, all of it moving as one single coherent thing, they say it has broken a different symmetry, a subtler one, something they label with the little tag U1, a phase symmetry. Don't worry about the name at all. The meaning underneath it is simply this: all the particles fall into perfect step, sharing one single rhythm, one unified motion, so that the whole liquid behaves like one enormous, gentle, unstoppable wave instead of a crowd of jostling separate things. That shared step is the flow, that is the frictionless current. So now you can hear the real shape of the dream those scientists wrote down. A supersolid would be matter that breaks both of these symmetries at the very same time. It would choose its places like a crystal and fall into perfect shared step like a superfluid. Order and flow. Stillness and current. Two symmetries broken at once in one quiet body of cold matter. Not a solid pretending to be a liquid, not a liquid hardening into a solid. Both genuinely together because each one is a different kind of breaking. And nothing says a single thing can't break in two ways at once. That's the rigorous version of the paradox we began with, the crystal that pours, written in the careful language of symmetry. And once you see it that way, it stops sounding like a contradiction at all and starts sounding almost inevitable. Of course, matter might do this. The frictionless flow was already real. The crystalline order was already real. The only question left was whether one humble piece of matter, somewhere, somehow, could be persuaded to hold both gifts at the same moment. For decades, that question hung in the cold air of the great helium laboratories, unanswered. The superfluid was right there, endlessly climbing its walls. The solid was right there, in any block of ordinary crystal. But the marriage of the two, the rigid current, the still flow, stayed a thing that lived only in equations and in the minds of a few daring people who refused to believe it was forbidden. And next, very slowly, we'll go and meet them. The first of them had a name almost nobody outside of physics knows, and yet what he wrote down in 1969 changed the shape of the entire search. Alexander Andreev was a Soviet physicist working in the tradition of the great Russian school of condensed matter, a tradition that had given the world Kapitsa himself and Lev Landau, and a long line of thinkers who were not afraid to ask whether the deep rules of quantum mechanics might conjure states of matter that ordinary experience would never prepare you to imagine. Andreev worked with a colleague named Ilya Lifshitz, and what the two of them did, in a paper that arrived quietly in the literature in 1969, was to take the structure of a quantum crystal and ask a genuinely strange question about the gaps inside it. Here is the thing about a real crystal. Any crystal, not just a quantum one. A crystal is a lattice of atoms arranged in a repeating pattern, like the tiles on a very patient floor that goes on for trillions and trillions of units in every direction. But real crystals are not perfect. They have defects. One of the most basic defects is simply a vacancy, a spot in the lattice where an atom is missing, a hole in the floor, a gap where a tile should be but isn't. In ordinary materials, these vacancies don't do much. They sit there, they might drift a little when the crystal is warm, they might interact with other imperfections, but they are essentially inert absences. Absences that don't have any dramatic character of their own. But Andreev and Lifshitz looked at vacancies in a quantum crystal and asked, what if the vacancies aren't just absences? What if, in a quantum world, the holes in the lattice are themselves particles, objects described by quantum wave functions, objects that can overlap, objects that have a quantum identity, and if they're quantum particles, then at cold enough temperatures, like all quantum particles of the right type, they might condense. You'll remember what condensation means in the language we've been building, slowly, together. When particles of a particular kind, bosons, particles that don't mind sharing the same quantum state, are cooled enough, they can all collapse into a single, shared quantum state. They stop being individuals. They become a single quantum object, a condensate. And a condensate flows without friction because there's nothing to disturb, no individuality to scatter against. What Andreev and Lifshitz were proposing was this. Inside a quantum crystal, the vacancies, the missing atoms, the holes, might condense. They might all fall into a single, shared quantum state. And if they do, they'd become a superfluid of holes flowing through the lattice from one gap to the next with no resistance at all. And here is the beautiful and strange thing. The crystal would still be there. The lattice of atoms would still hold its repeating order, its rigid arrangement, its translational symmetry broken. Nothing about the macroscopic solid structure would change. But threading through that structure, living inside the holes in the floor, there would be a frictionless current, an invisible river of quantum gaps flowing without effort. The solid part and the superfluid part would coexist, each in its own domain, the atoms keeping their places, the vacancies flowing free. That is the vacancy picture of supersolidity. And it is the first time anyone wrote down in careful physics what a supersolid might actually be and where it might actually be found. A year later, independently, the English physicist Anthony Leggett turned the same idea over in his hands and came at it from a different angle. Leggett, who would go on to receive the Nobel Prize in 2003 for unrelated work on superfluidity, was interested not just in the mechanism but in the signature, the measurable trace that a supersolid would leave in an experiment, the mark that would prove it was real. He introduced a concept he called non-classical rotational inertia, NCRI as it came to be known. The idea is lovely in its simplicity, and it's worth walking through it here because it becomes important later, both when something appears to confirm it and when that something quietly falls apart. Think about a spinning object, a solid cylinder, say, or a container. When you spin it, the matter inside it spins with it. Solid matter rotates as a single body. If you speed up the rotation or slow it down, the whole thing responds together. The moment of inertia and the quantity that measures how much a body resists changes in its rotation, depends on how much matter is present and where it is. More mass further out from the center means a higher moment of inertia. That's the classical picture, and for most materials it is simply and completely correct. But a superfluid doesn't behave this way. A superfluid has a quantum phase coherence, a single shared rhythm. And when you try to spin it, at least at low enough angular velocities, it doesn't rotate with the container. It stays still, it decouples, and because it decouples, the effective moment of inertia of the system drops. There is less stuff apparently rotating. The container's inertia behaves as though part of the mass has simply vanished. Leggett said, if you had a supersolid, a solid that also carries a superfluid fraction, then you would see exactly this. Some fraction of the solid's mass, and the fraction that was flowing freely like a superfluid, would not rotate with the bulk. The effective rotational inertia of the sample would be lower than you'd expect for a simple solid. Non-classical because it defies the classical accounting of mass in rotation. The size of the drop would tell you the superfluid fraction, how much of the solid was genuinely flowing. This was a gift, a concrete, measurable prediction, not just a theorist's dream, but a number you could, in principle, go and measure. If you built a very precise torsional oscillator, a device that spins a container back and forth and measures exactly how it responds, and you put a candidate supersolid inside it, and you cooled it down, and you watched the moment of inertia carefully as the temperature dropped, you might see a sudden dip, a signature, the ghost of the frictionless fraction. All you needed was the right material, and here, of course, the eyes of physicists turned toward helium. Helium-4 is the textbook quantum material. You already know its superfluid life below the lambda point, that remarkable transition at roughly 2.17 Kelvin, where viscosity simply vanishes and the liquid climbs its walls and spins in rings that never stop. Below that temperature, liquid helium-4 is a superfluid, a fully quantum liquid. But the question of supersolidity requires a solid, and here helium presents a peculiarity that is, in its own quiet way, just as strange as anything we've discussed tonight. Under ordinary pressure, the pressure of the air in this room, or wherever you are right now, helium never becomes solid. Not at any temperature, not even at absolute zero itself. You could cool helium down to 0 Kelvin, as close as physics allows, and it would still be a liquid. The reason is quantum mechanical. Helium atoms are so light and the forces between them so weak that quantum zero-point motion, the irreducible, unavoidable jiggling that quantum mechanics says everything must have even at its lowest energy, keeps the atoms moving enough to prevent them locking into a lattice. The zero-point energy is greater than the binding energy of the solid. The quantum fuzziness wins. Helium refuses to solidify. If you want solid helium, you have to squeeze it. You have to apply pressure from outside, around 25 atmospheres worth, roughly 25 times the pressure of the air around you, to force the atoms close enough together that the lattice can hold. Only then, compressed and cold, does helium-4 finally consent to become a solid. And the resulting solid is, in quantum terms, still extraordinarily soft and lively. Its atoms are barely touching. The lattice is loose. The zero-point motion is still large, and that means the vacancies, those quantum gaps that Andreev and Lifshitz were thinking about, might be particularly free, particularly mobile, particularly quantum. So solid helium-4, pressed to around 25 atmospheres and cooled to temperatures close to absolute zero, became the natural hunting ground for the supersolid. It was the most quantum solid anyone knew how to make. If the supersolid existed anywhere, it seemed to live here, in this strange compressed crystal, this material that had to be argued into holding its shape. For decades, the search went on. Experiments were refined. The torsional oscillator became the standard instrument. Physicists built ever more sensitive versions of it, ever more careful, ever more shielded from outside vibration and interference. They cooled their samples to within tiny fractions of a Kelvin from absolute zero. They looked for the dip. They looked for the non-classical rotational inertia. Year after year, they did not find it cleanly. The supersolid remained in the equations, patient, theoretical, waiting. And then in 2004, everything seemed to change. Yoon Seong Kim was a graduate student at Penn State. His advisor was Moses Chan, one of the most respected low-temperature physicists in the world. Together they built a torsional oscillator of exceptional precision, filled it with solid helium-4, squeezed and cooled to the right conditions, and watched. What they saw stopped them. As the temperature dropped below about 200 millikelvin, roughly a fifth of a degree above absolute zero, the apparent moment of inertia of the sample dropped, not by much, about 1 to 2% of the total. But it dropped, cleanly, reproducibly, exactly as Leggett had predicted the NCRI signature would look. A fraction of the solid helium seemed to stop rotating with the container, as though it had decoupled, as though it had become, or was hosting, a superfluid fraction. The announcement rippled through the physics community with rare speed. Here, at last, was the signal. 35 years after the theoretical prediction, solid helium-4 was apparently showing the fingerprint of supersolidity. The headlines were careful but unmistakably excited. This was a candidate for a new state of matter. Moses Chan, who had spent his career working in this quiet corner of low-temperature physics, was cautious and thorough in the way good experimentalists always are. But the data looked real. The dip was there. Kim and Chan published in Science in January 2004, and the result was immediately hailed as one of the most significant condensed matter discoveries in years. Other groups around the world rushed to repeat the measurement. Some did see similar anomalies. The dream of the supersolid, held in the cold waiting of the helium laboratories for so long, seemed to have finally arrived. But physics is patient, and physics does not grant prizes simply for the appearance of a signal. In the years that followed, people looked more carefully. And a different physicist with a different kind of instrument started asking a different kind of question. John Beamish, working at the University of Alberta, was interested in the mechanical properties of solid helium, not its rotational behavior, but its elastic stiffness, how rigid it was, how it responded to a shearing force. And when he measured the shear modulus of solid helium-4, its resistance to being twisted as a function of temperature, he found something. The shear modulus of solid helium-4 also changed below about 200 millikelvin. It stiffened. the solid became slightly more rigid at exactly the temperatures where the torsional oscillator was showing the NCRI anomaly. This matters because a torsional oscillator is itself a mechanical system. The way it responds depends not just on the mass and its distribution, but on the stiffness of the material it contains. A stiffer material transmits force differently, and if the helium was getting stiffer at low temperatures, the oscillator would behave differently. The period of oscillation would change in a way that could look, to a casual analysis, like a drop in effective moment of inertia. It wasn't that some fraction of the mass had decoupled, it was that the mechanical coupling between the helium and the container was changing. The solid was stiffening. But why was the helium stiffening? Here the story goes one layer deeper, and it requires us to mention a particular kind of impurity. Natural helium-4 always contains tiny amounts of helium-3, a different isotope of helium with 3 nuclear particles instead of 4. Helium-3 is lighter, behaves differently at low temperatures, and is present at the level of parts per million in commercial helium. In a quantum solid, these helium-3 impurities can attach themselves to dislocations, line defects in the crystal, like a row of misaligned tiles running through the lattice. At higher temperatures, the impurities are mobile, and the dislocations can slide, and the crystal is relatively soft. But at very low temperatures, the helium-3 atoms freeze onto the dislocations, pinning them, preventing them from moving. The crystal stiffens. This pinning mechanism, the dislocations bound by helium-3 impurities, explained the shear modulus anomaly. And if it explained the shear modulus anomaly, and the shear modulus anomaly explained the torsional oscillator anomaly, then the original NCRI signal might not be NCRI at all. It might be a mechanical mimic, a solid stiffening for mundane reasons, wearing the clothes of a superfluid. The test was clean and damning. Beamish and collaborators measured samples with different concentrations of helium-3. The anomaly changed in size in exactly the way the mechanical explanation predicted. It did not change in the way the supersolid explanation would have required. Moses Chan, to his great credit, did not resist the new evidence. He went back to the experiment. He rebuilt it with more careful controls, used samples with lower helium-3 concentrations, designed the oscillator to better separate mechanical and inertial effects. And in experiments published around 2012, he found that when the mechanical contributions were properly accounted for, the supersolid signal in solid helium-4 essentially vanished. What remained was consistent with zero. The NCRI, cleaned of its mechanical impersonator, was gone. The announcement was quiet. There were no headlines to match the 2004 excitement. The supersolid in helium had not been found. It had been a shadow cast by a subtler effect. A brave and careful ghost that turned out, on closer inspection, to be a stiff crystal and some frozen impurities. It is worth sitting with that for a moment. 35 years of searching, a signal that looked for 8 years like it might be real, and then the patient undoing, not by a rival experiment, but by the original experimenter himself, turning back to his own data with fresh instruments and a willingness to be wrong. That is what the long search looks like from the inside. Not a clean story of discovery, but a careful conversation between a prediction and an instrument, where sometimes the instrument is speaking about itself. And after 2012, solid helium-4 supersolidity remained, and still remains, unconfirmed. The vacancy picture that Andreev and Lifshitz built so carefully, the NCRI fingerprint that Leggett handed to experimentalists as a gift, had not yet found their material. The theory was sound, the experiments were honest, but the marriage of rigid order and frictionless flow in the helium crystal had so far refused to happen, or at least refused to be seen. So the community did what communities do when a particular path seems blocked. It looked for another one. If solid helium-4 wouldn't cooperate, perhaps the supersolid could be reached from the other direction. Not by starting with a crystal and trying to put flow in it, but by starting with a superfluid and trying to put order in it. Start with a Bose-Einstein condensate, an existing superfluid already phase-coherent, already flowing without friction, and ask whether you could persuade it to develop a crystalline density pattern, to choose its places, to break translational symmetry while keeping the superfluid phase intact. This required a particular kind of interaction, a standard Bose-Einstein condensate, the kind that Eric Cornell and Carl Wyman first made in Boulder, Colorado in 1995, using rubidium atoms, and the kind that Wolfgang Ketterle made a few months later in Cambridge using sodium. Those early condensates had what physicists call contact interactions, short-range forces. Two atoms bouncing off each other only when they were essentially touching. And contact interactions on their own don't produce crystalline order in a condensate. They smear the density out uniformly. The condensate is a superfluid, but a smooth one, without the density modulations that would mark it as also a crystal. For those early condensates, Cornell and Wyman and Ketterle won the Nobel Prize in 2001. They had achieved something remarkable. Matter cooled to temperatures measured in nanokelvin, billionths of a degree above absolute zero, far colder than the heart of any star, far colder than the emptiness between the galaxies. A few thousand rubidium atoms, or sodium atoms, held in a magnetic trap and cooled by lasers and evaporative cooling until they slipped together into a single quantum wave. A superfluid, a condensate, something that had never existed in the universe before humans learned to make it. But a condensate with just contact interactions would not spontaneously modulate. It would not crystallize. To get a supersolid, you needed something extra. A force that could reach across the condensate, pull it into lumps, coax it into choosing periodic density variations, while the quantum coherence kept the whole thing unified. You needed a long-range interaction. Two different approaches appeared in 2017, nearly simultaneously, in the pages of Nature. At ETH Zurich, Tilman Esslinger's group did something elegant and indirect. They took a Bose-Einstein condensate and placed it inside an optical cavity, a resonator built from carefully aligned mirrors that could trap light and force it back and forth through the condensate many times. In fact, they used two optical cavities intersecting. The photons bouncing inside those cavities interacted with the atoms in the condensate. And through this light-mediated interaction, atoms affecting photons, photons affecting atoms, the whole system developing a mutual conversation, the condensate developed a density pattern, a spatial modulation, bright spots and dark spots arranged with a crystalline regularity imprinted by the geometry of the light fields. The self-organized pattern coexisted with the superfluid coherence. It was supersolid behavior of a kind. The crystalline order was there because the cavities imposed it. The superfluid phase was there because the condensate was still a condensate. Both were real, but the pattern required the cavities to exist, removed the light, and the order was gone. In this sense, it was not quite a freestanding, intrinsic supersolid, but a supersolid created and sustained by external fields. At MIT in the same year, Wolfgang Ketterle's group took a different approach. Spin-orbit coupling, a technique from the toolkit of quantum simulation, where lasers are used to entangle the internal spin states of the atoms with their momentum, can produce exotic phases of matter in ultra-cold gases. Ketterle's group used this to create what are called stripe phases in their condensate, density modulations oriented in a particular direction, periodically varying, coexisting with the superfluid order. Again, both symmetries were broken at once, translational and phase. Again, supersolid behavior. Solid. Both papers appeared in Nature in March 2017, and together they were a signal, not conclusive, because the cavity-enforced and spin-orbit methods both had external elements driving the pattern, but unmistakable. The physics was real, the dual symmetry breaking was real, and the community now knew it was possible to reach the supersolid not through helium's crystal descending toward flow, but through the condensate's flow ascending toward order. The truly intrinsic supersolid, one where the crystalline order arose from the atom's own interactions with each other, requiring no external patterning, was waiting one more step ahead, and the tool that made it possible was magnetism. Not the magnetism of iron or lodestones, but a far subtler kind. Some atoms, when you look at them closely, are highly magnetic. They carry a large magnetic dipole moment, a small compass needle built into their quantum structure. And two magnetic dipoles don't just interact when they're touching, they feel each other across distance. The force between them depends on both how far apart they are and what direction they're pointing. It's anisotropic, meaning it's different in different directions, and it's long range in the way contact forces are not. The atoms that carry this property most strongly, and that experimentalists learned to cool and condense in the right years, were dysprosium and erbium. Both rare earth elements, both extraordinarily magnetic by atomic standards. The magnetic dipole moment of dysprosium in particular is among the largest of any atom, 10 Bohr magnetons or more, depending on the state. When you make a Bose-Einstein condensate from these atoms, the dipole-dipole interactions between them are strong enough to matter, to reshape the condensate, to compete with the contact interactions and produce something new. What the dipolar condensate did, when cooled to the right temperatures and released from its trap at the right densities, was extraordinary in its quiet way. The condensate did not spread into a uniform cloud. Instead, it broke apart into discrete lumps. A small number of them, typically, a handful of quantum droplets, each one a tiny dense island, arrayed in a line or a small cluster with a regular spacing. A self-bound array, held together not by an external trap, but by the balance of attractive dipolar forces and repulsive contact forces, and a quantum effect called quantum fluctuations, which prevented each droplet from collapsing inward. On first glance, this looks like the condensate breaking into separate pieces, or like water droplets separating from a stream. But here is the profound part. The droplets were not separate. They shared a single quantum phase. If you measured the quantum mechanical phase of the condensate, that angle, that step in the shared march, that U1 symmetry we discussed, you found the same value in every droplet. They were all in step. The superfluid coherence was global, spanning all the droplets at once, even though the density was not uniform. Each droplet was its own little island of high density, but all the islands were part of the same quantum wave. Crystalline order, yes. The droplets were spaced periodically, breaking translational symmetry. Superfluid coherence, yes. A single shared phase across all of them, the U1 symmetry broken in the same way everywhere, both at once, intrinsically, arising from the atom's own interactions. 3 groups saw this in 2019 within months of each other, a convergence that in physics is often a signal that a discovery is real and that the field was ripe for it. The group in Pisa, the group in Stuttgart led by Tilman Pfau, and the group in Innsbruck led by Francesca Feleno, all working with dipolar atoms, all observing the self-bound droplet arrays, all measuring the signatures of dual symmetry breaking. It is generally regarded as the first robust experimental realization of a supersolid in the laboratory. Stop for a moment and let the scale of it settle. These experiments were happening at temperatures in the nanokelvin range. 1 nanokelvin is 1/1000th of a degree above absolute zero. Absolute zero is minus 273.15 degrees Celsius, already a number that defies ordinary experience. A nanokelvin below that means you are at a distance from absolute zero that is to a single degree what a millimeter is to 1,000 kilometers. The coldest known regions of deep space, the vast, dark clouds of gas between the galaxies, sit at around 2 to 3 Kelvin, billions of times warmer than these experiments. This is not a poetic exaggeration. The dipolar supersolid samples were and are among the coldest matter ever assembled in the history of the universe, cooled not by any natural process, but by the extraordinary ingenuity of people in laboratories using lasers and magnetic fields and patience. And the samples themselves were fragile and tiny, not a block of crystal you could hold, not even a speck you could see with a naked eye. A few thousand atoms, or tens of thousands at most, arranged in an array of perhaps 3 to 5 droplets, each one a quantum puff of matter that would expand into a cloud the instant the trap was released. The entire structure, this genuine supersolid, this first real marriage of crystal and superfluid, existed for fractions of a second in a cryostat the size of a room before being destroyed by its own expansion and photographed in the act of falling apart. The photograph was the data. Absorption imaging, shining a laser through the expanding cloud and capturing the shadow, revealed the interference pattern of the droplets, the fringe spacing telling you the lattice constant of the crystal, the visibility of the fringes telling you the coherence of the superfluid phase, both pieces of information in the same image, both symmetries visible at once. And alongside the imaging, there was the second way to confirm the dual nature, the secret handshake that Leggett and others had predicted would be the smoking proof. The sound modes. In a normal superfluid, disturb it slightly and it rings like a single bell, a single mode of collective oscillation, the quantum waves sloshing back and forth. In a normal crystal, displace the atoms from their lattice sites and you get phonons, sound waves carried by the periodic structure like vibrations in a spring mattice. But in a supersolid, a material that is both at once, there are two sets of oscillations, two distinct ways the matter can move collectively. One is the motion of the crystal, the droplets moving in and out, the density modulation oscillating, the translational symmetry doing its ringing. The other is the motion of the superfluid phase, the quantum angle oscillating, the U1 symmetry doing its ringing. These are called the two Goldstone modes, named for the theoretical framework that says every spontaneously broken continuous symmetry comes with a massless collective oscillation. Two broken symmetries, two Goldstone modes, two distinct sounds, measuring both sounds in the dipolar supersolids, reported in papers in the years following 2019, with the clearest results coming around 2021, was the deepest confirmation available. Not just the density pattern, not just the coherence, but the independent vibrations of both aspects of the double nature. A material ringing in two keys at once because it was truly, simultaneously, both things. And yet, and this is the thread that keeps the whole story moving forward rather than ending here, in the cold of an Innsbruck laboratory, even with all of this, the dipolar supersolid had a fundamental constraint built into it. It was cold. Extraordinarily, almost incomprehensibly cold. The nanokelvin refrigeration was not incidental to the experiment. It was the condition of the experiment. Remove the cooling even slightly and the condensate warmed, the quantum coherence was destroyed by thermal fluctuations, the droplet array melted away, and the supersolid ceased to exist. This meant the dipolar supersolid was, in a real and practical sense, trapped. Trapped in the laboratory, trapped behind an enormous wall of technical infrastructure, dilution refrigerators, vacuum systems, laser systems of extraordinary sophistication and expense that would always be required, as long as the supersolid was made from atoms that needed to be cooled to within a billionth of a degree of absolute zero. The search had reached something real. But the something real was extraordinarily fragile and extraordinarily cold. And somewhere in the mind of a different community of physicists, people who worked not with ultra-cold atoms, but with light and semiconductors and the quantum behavior of matter in a very different regime, a different possibility was quietly taking shape. What if the supersolid didn't have to be cold? What if there was a kind of matter that could condense and crystallize and flow all at room temperature or something much closer to it? What if the key was not to make atoms cold enough to be quantum, but to use something that was already quantum by its nature, something so light, so fast, so inherently wave-like that it existed in a quantum state without needing a refrigerator at all? The answer to that question would come from a material that seems at first to have nothing to do with condensed matter at all. It would come from light itself, from photons, the smallest packets of the electromagnetic field, the quanta of light, massless particles that travel at the universal speed limit and carry no charge, and, in a vacuum, interact with nothing else at all. The idea that you could make a supersolid from light sounds even now like a category error. Photons don't have mass, they don't have a rest frame. In free space, two photons pass through each other as if neither exists. How could light, of all things, form a crystal? How could it flow without friction? How could it be a supersolid? The answer starts with a word that physicists in semiconductor labs had been working with for decades: polariton. And it is there, in the semiconductor laboratories of southern Italy, in March of 2025, that the hunt for the supersolid finally reached a place nobody, not Andreev, not Lifshitz, not Leggett, writing carefully in 1970, had thought to look. But we'll get there slowly, because the story of the polariton is worth understanding from the beginning, and because the beginning explains why everything about it seems, at first, impossible. So let us go back for a moment to the rooms where the search continued after helium had given up its secrets. Or rather, after helium had offered what looked like a secret, and then quietly taken it back. The year is 1995. The place is the Joint Institute for Laboratory Astrophysics in Boulder, Colorado, and also, simultaneously, a few months later, the campus of the Massachusetts Institute of Technology in Cambridge. Two groups of scientists working independently are about to do something that had never been done before, something that Bose and Einstein had predicted in the 1920s, and that most people, for most of those intervening decades, had assumed was probably impossible in practice, even if mathematically sound. They are going to cool a gas of atoms so far below any temperature naturally occurring in the universe that the atoms stop behaving like individual particles and start behaving like a single, shared, wave-like thing. Carl Wieman and Eric Cornell at Boulder used rubidium. Wolfgang Ketteler at MIT used sodium. The temperatures they reached were measured not in Kelvin, but in nanokelvin, billionths of a single degree above absolute zero. To give you a sense of what that means, the surface of the Sun is around 6,000 Kelvin. The coldest reaches of interstellar space, the molecular clouds drifting between the stars, are about 3 Kelvin, barely above absolute zero. These atoms in Colorado and Massachusetts were 1,000 times colder than interstellar space, 1,000,000 times colder in places. They had entered a regime of cold so extreme it simply does not occur anywhere in the natural universe as far as we know. It had to be engineered, coaxed into existence by lasers and magnetic fields and years of incremental refinement. And when the temperature fell low enough, something extraordinary happened. The atoms, which had been behaving as a cloud of separate particles with separate quantum states, suddenly snapped together into a single collective quantum state. All of them, at once. a gas of thousands or millions of atoms began to behave as though it were a single quantum object. One enormous matter wave extended across the trap, with a single wave function describing all of them together. This was the Bose-Einstein condensate, and it had been predicted by Satyendranath Bose and Albert Einstein in 1924 and 1925 without either of them being remotely sure it could exist in the laboratory. Cornell, Wieman, and Ketteler shared the Nobel Prize in Physics in 2001 for showing that it could. Now, a Bose-Einstein condensate is, by its very nature, already a superfluid. The atoms in a Beck all share the same quantum phase, the same rhythm, you might say, the same heartbeat, and that shared coherence means they flow without the usual kind of friction. Impurities, defects, the random jostling of thermal motion, all the things that would ordinarily impede a flowing fluid, have almost no effect because the whole cloud is marching to the same quantum beat. Superfluid flow in a Beck is not a tendency or an approximation, it is a consequence of the condensate's mathematical nature. It is baked in. So the Beck researchers of the late 1990s and early 2000s had a superfluid already. What they did not have was the other half. They had the frictionless flow. They did not have the crystalline order. For a supersolid, you need both. You need the atoms to arrange themselves in a periodic pattern, like a crystal, while simultaneously flowing without friction. And in an ordinary BEC, the atoms spread themselves through the trap as smoothly as possible, as evenly as they can, avoiding any kind of density modulation. The wave function is smooth, the cloud is featureless. There is no crystal because the interactions between the atom, which are weak and short range, pushing neighbors apart without much else, give no reason for the atoms to bunch into a regular pattern. What the supersolid hunters needed was a Beck that could, under the right conditions, choose to organize itself. To spontaneously develop a striped or spotted texture, a periodic pattern of denser and less dense regions, while keeping the underlying quantum coherence of the condensate intact. This is delicate. It is delicate because the thing you are trying to add, spatial order, tends to destroy the thing you are trying to preserve. In a crystal, atoms are pinned to specific sites by their interactions with their neighbors. They lose their quantum mobility, they settle. And the moment atoms settle into fixed positions, the shared quantum coherence that makes the condensate a superfluid starts to erode. The crystal wants to freeze the atoms. The superfluid wants to free them. Getting them to do both at once is not just an experimental challenge. It is in some ways a conceptual challenge. You have to build a system in which the tendencies toward order and toward flow are not enemies but partners. It took until 2017 for the first real progress to arrive, and it came from two directions at once, which is often how physics works when a problem has been hanging just at the edge of solvability for a long time. The first direction came from Zurich. Tilman Esslinger and his group at ETH Zurich had spent years studying what happens when you place a Bose-Einstein condensate inside an optical cavity, a pair of highly reflective mirrors that trap light between them and force it to interact over and over with the atoms sitting in the middle. Ordinarily, a Beck sits in a trap and its atoms interact with each other and with their environment, but the photons of the trapping laser simply pass through. In an optical cavity, the photons bounce back and forth, hitting the atoms again and again, building up a kind of sustained, structured conversation between the light and the cloud. The atoms and the light begin to influence each other, and under the right conditions, the system finds a new kind of equilibrium, one in which the atoms spontaneously arrange into a regular pattern, a kind of crystal imposed not by direct atom-atom interactions, but by the collective back and forth with the cavity light. The cloud develops texture, it develops order. What Esslinger's group did in 2017 was to use not one optical cavity, but two, a beck placed at the intersection of two crossed cavities so that the light could impose structure in two perpendicular directions at once. The condensate, driven by a laser and interacting with both cavities simultaneously, organized itself into a checkerboard-like density pattern. It spontaneously broke translational symmetry. The atoms chose positions they bunched into a lattice, while keeping the superfluid coherence of the condensate. There was crystalline order, there was superfluid flow. The two were present at once. The paper appeared in Nature in March 2017, and it described, carefully and precisely, a system that satisfied the defining criteria of supersolidity. In the same issue of Nature, almost simultaneously, Wolfgang Ketterle's group at MIT reported a different route to the same destination. Ketterle, one of the pioneers of the BEC itself, one of the men in the room in 1995 when it first became real, had spent the intervening years pushing the condensate into new regimes. His team used a technique called spin-orbit coupling. They applied carefully tuned laser fields to the atoms in their BEC in such a way that the atom's internal quantum states, their spin, a quantum mechanical property, became tied to their momentum. When the spin and the momentum are linked in this way, the condensate finds that it can lower its energy by developing a striped pattern, alternating bands of atoms with slightly different spins and momenta, like the stripes on a flag. These stripe phases, as they are called, also satisfy the dual criteria. There is a spatial periodicity, a crystal-like arrangement, and the underlying coherence of the condensate is maintained. Superfluid flow persists through the stripes. Both results were real, both were carefully checked, but both results, the cavity route from Zurich and the spin-orbit route from MIT, had a character that some physicists described as slightly externally imposed. The Zurich condensate developed its pattern because the cavities were driving it into that arrangement. Remove the cavities and the pattern goes. The MIT stripe phases depended on precisely tuned laser fields that were continuously applied. These are supersolids in the sense that the criteria are met, but they are supersolids that require some external scaffolding to maintain their crystalline character. The question remained, could you have a supersolid that organized itself purely from within? Could you have a crystal that arose not because something external was imposing a pattern, but because the interactions between the particles themselves demanded it? That is what the 2019 results provided, and they arrived in a rush from 3 laboratories almost simultaneously. The key was a different kind of atom. Ordinary atoms, the ones used in most BEC experiments, rubidium, sodium, potassium, interact with each other through forces that are short-range and, in the quantum gas context, essentially isotropic. They push their nearest neighbors away equally in all directions, like tiny springs. These contact interactions are the workhorse of cold atom physics, and they are enormously useful, but they do not, on their own, generate the kind of structured long-range competition that produces spontaneous crystallization in a superfluid. For that, you need interactions that extend further, that reach across the gas and create competing tendencies, some pushing the atoms apart at short range and some pulling them together at longer range, so that the system has to negotiate between these competing forces and finds, in that negotiation, a compromise state that is neither uniformly spread nor uniformly collapsed. Long-range, anisotropic interactions. There is a class of atoms that have them. They are the most magnetic atoms in the periodic table, atoms whose unpaired electrons give them enormous magnetic dipole moments, so large that the magnetic force between two such atoms oriented in the right direction becomes comparable to or even dominant over the usual short-range contact interactions. Dysprosium, erbium. These are rare earth elements, heavy and complex, not the first atoms you would think to cool to a nanokelvin. But their magnetic moments are exceptional, and in the late 2010s, several groups around the world had mastered the difficult art of making BECs from them. A magnetic dipole-dipole interaction is directional. Two magnets aligned head to tail attract each other. Two magnets aligned side by side repel. This directionality means that the interaction depends not just on how far apart two atoms are, but on the angle between them and the external magnetic field that sets the direction of their dipoles. In a gas of magnetic atoms, this creates a complicated anisotropic energy landscape. And in the right parameter regime, a remarkable thing happens. The gas, which started as a smooth BEC, spontaneously breaks up. It does not spread smoothly through the trap. It does not collapse into a single lump. Instead, it organizes itself into a regular array of small, dense droplets, tiny, self-bound blobs of matter, each one a concentrated region of atoms arranged in a periodic pattern like pearls on a string, or like a row of small islands, each island separate, but each island sharing the same quantum phase as all the others. That last detail, the shared quantum phase, is the crucial one. Each droplet is dense, each droplet is localized. Together they form an array with crystalline order, a periodic structure, a broken translational symmetry. But they are not separate, they are not independent. The quantum mechanical wave function of the condensate extends across all of them simultaneously, connecting them with a single, coherent phase. The whole array is one quantum object. The atoms can tunnel between the droplets, flowing through the barriers between them with zero friction because the whole system is still, at the quantum mechanical level, a single, coherent condensate. Crystalline order and superfluid coherence, together, intrinsically, arising from the physics of the atoms themselves without any external scaffolding to hold them in place. This is the dipolar supersolid. Three groups saw it at nearly the same moment. In Pisa, a collaboration connected to a long tradition of Italian cold atom physics reported the droplet array in strongly magnetic erbium and dysprosium condensates. In Stuttgart, Tilman Pfau's group, who had pioneered much of the physics of strongly magnetic quantum gases over the preceding decade, saw it in their dysprosium condensate. In Innsbruck, Francesca Fellaino's group, who had been working with both erbium and dysprosium for years, reported their results as well. Three different laboratories, three different groups of people, all working on the same physics at the same time, all arriving at the same answer in the same year. This kind of near-simultaneous convergence happens in physics when a problem is ripe, when the tools have finally caught up with the question. 2019 was the year the tools caught up. There is something quietly remarkable about the conditions under which this happened. The temperatures involved are not just cold, they are cold in a way that requires some effort to hold in your mind. Absolute zero is 0 Kelvin, which is negative 273.15 degrees Celsius. It is the temperature at which all thermal motion ceases. The theoretical floor, the coldest anything can be. The atoms in these dipolar supersolid experiments were held within a few billionths of a degree of that floor. A nanokelvin is 1/1 billionth of a Kelvin. The coldest these experiments ran was a handful of nanokelvin. If you imagine the temperature scale from absolute zero to the surface of the sun as a staircase of 6,000 steps. These experiments were sitting on the bottom step, a fraction of a single step's height above the ground floor. The interstellar medium, the gas between the stars, the diffuse clouds of hydrogen drifting in the dark between galactic arms, is at about 3 Kelvin. That sounds cold, and it is compared to anything we encounter in daily life. But 3 Kelvin is 3 billion nanokelvin. The dipolar supersolid experiments were 1 billion times colder than interstellar space. Colder, in that sense, than anything the universe produces on its own. This is entirely human-made cold, engineered in a laboratory the size of a large room, sustained by laser cooling and magnetic trapping and decades of accumulated expertise in keeping fragile quantum states alive long enough to measure them, and the structure itself, the supersolid crystal, was gossamer, not a block, not a slab, an array of a handful of droplets, perhaps 10 or 20 tiny dense blobs of atoms strung in a line, each droplet containing maybe a few thousand atoms, the whole array stretching across a distance smaller than a human hair. If you tried to pick it up, it would not exist. The moment the magnetic field that holds it in place changed, the moment the laser that cools it turned off, the supersolid would vanish, its atoms dispersing, its quantum coherence evaporating in a fraction of a second. It lives only in the controlled quiet of the trap, in the dark of the vacuum chamber, sustained by nothing except the precise balance of competing quantum forces. And yet it is real. It is, as far as we know, the first intrinsic supersolid, the first system in which the supersolid state arises from the fundamental properties of the matter itself without being imposed from outside. And the experiments that confirmed it went beyond simply seeing the droplet array. They went further to the thing that physicists call the secret handshake, the proof that cuts through ambiguity and shows you unambiguously that you are looking at something with two truly distinct kinds of order coexisting at once. The secret handshake is sound, not sound in the ordinary sense, not pressure waves in air, sound in the condensed matter sense, collective oscillations of the matter, waves that carry information about the system's internal structure and the symmetries it has broken. In an ordinary superfluid, a beck without crystalline order, there is one kind of sound. Physicists call it the Bogolyubov mode, or the phonon mode of the condensate, a compression wave, atoms moving together and apart, the condensate breathing in and out. One mode, one frequency, one kind of collective motion, but a supersolid has broken two symmetries. It has broken translational symmetry, giving it the periodic lattice of the crystal. And it has broken U1 phase symmetry, the symmetry associated with the overall quantum phase of the condensate, giving it the superfluid fraction. When a continuous symmetry is broken, something very general happens, something that falls out of the mathematics of quantum field theory, whether you are talking about a magnet or a crystal or a superfluid or a particle in a high-energy accelerator. When a continuous symmetry is broken, there is always, with no exceptions, a corresponding low-energy collective mode, a massless excitation, a wave that costs almost nothing to create. Physicists call these Goldstone modes, after Jeffrey Goldstone, who described the general principle in 1961, one broken symmetry, one Goldstone mode, two broken symmetries, and a supersolid breaks, two of them simultaneously, two Goldstone modes, two distinct collective oscillations of the matter, each associated with one of the two broken symmetries, each carrying a different frequency signature, each traveling at a different speed through the material. In an ordinary superfluid with crystalline order but no superfluid fraction, you would find crystal phonons, the sound of the lattice. In an ordinary superfluid with no crystalline order, you would find the condensate's breathing mode, the sound of the phase. In a supersolid, you find both at once, traveling through the same few thousand atoms. Two kinds of sound. Two distinct collective modes. Two Goldstone bosons coexisting in the same material, each one the ringing of a different broken symmetry. This is what the groups in Pisa, Stuttgart and Innsbruck measured in the period around 2019 to 2021. As the dipolar supersolid experiments matured, they excited their droplet arrays with small perturbations and watched how the system responded, how the density oscillated, how the phase evolved. And they found, unmistakably, the two modes. The crystal mode, the droplets bouncing, spacing, oscillating, the lattice ringing, and the superfluid mode, the overall phase of the condensate oscillating, the superfluid fraction sloshing gently back and forth through the crystal. Two sounds in the same matter, the secret handshake confirmed. It is worth pausing here for a moment because this is not an obvious thing. Think about it this way. Imagine a piece of ice, a crystal of water molecules, locked in place in a hexagonal lattice. Tap it with a tuning fork and it will ring, and the ring will carry information about the stiffness of the lattice, the mass of the water molecules, the forces between them. That is crystal sound, one kind of oscillation arising from one kind of order. Now imagine that same ice somehow also had a superfluid fraction, a fraction of the water molecules that were not individually localized but were delocalized across the whole crystal, flowing without friction through the spaces between the lattice sites. That superfluid fraction would have its own kind of oscillation, its own collective mode, ringing at a different frequency, carrying information about the coherence of the flowing fraction rather than the stiffness of the lattice, both sounds at once in the same material. That is roughly what the dipolar supersolid experiments detected, not in water, obviously, not at room temperature, but in a gas of a few thousand magnetic atoms at a nanokelvin, and the detection was precise and unambiguous. There is one more thing to say about the dipolar supersolid, and it concerns the relationship between what was finally found and what was originally predicted. Andreev and Lifshitz in 1969 imagined something specific, a quantum crystal, solid helium, they had in mind, in which the vacancies, the missing atoms, the holes in the lattice might Bose condense and flow. The crystal was to be the starting point, already solid, already ordered, and the superfluid fraction was to arise from quantum defects tunneling through it. Leggett's analysis in 1970 was also framed this way: non-classical rotational inertia as the signature of a condensed vacancy flow superimposed on an otherwise conventional solid. The original picture was a lattice that already existed, with a quantum fluid threading through its holes. The dipolar supersolid does not work that way. There are no vacancies threading through a pre-existing crystal. There is no solid to begin with. The whole thing starts as a superfluid, a smooth, coherent condensate. And it is the competition between competing interactions, the long-range magnetic forces pulling the atoms together at certain distances and pushing them apart at others, that drives the condensate to spontaneously develop crystalline order. The crystal grows out of the superfluid, not the other way around. The order and the coherence arise together from the same physics in the same moment. Physicists describe this as interaction-driven supersolidity. The supersolid state emerges because the interactions between the particles make it energetically favorable, not because a pre-existing crystal happens to have quantum vacancies. This is a meaningful conceptual distinction. It means that the theoretical framework Andreev, Lifshitz, and Leggett built in the late 1960s and 1970, which is beautiful and original and genuinely important, is not the mechanism that produces the supersolids we have actually observed in the laboratory. Nature found a different route. It found a route that the original theorists did not map, and that the experiments of the 2010s and 2019 opened up. The prediction that matter could be simultaneously solid and superfluid, that prediction was right. The specific mechanism the predictors imagined, that turned out to be just one possibility among others, and not the one the universe chose to show us first. This is perhaps a more honest and more interesting outcome than if everything had worked out exactly as predicted. It means the landscape is richer than the original map suggested. It means there are more ways to be a supersolid than anyone knew in 1970. And it means, in particular, that the question physicists started asking more urgently in the 2010s was not merely idle curiosity, but a direct challenge to the known map. If supersolidity is interaction-driven, if the key is the right kind of competition between forces eating, then what other platforms might support it? What other systems might host the coexistence of order and flow? Did it have to be atoms? Did it have to be matter at all? Let that question rest there for a moment. The way the dipolar droplets rest in their magnetic trap, suspended, precise, almost impossibly fragile, and entirely real. Because the answer to that question, when it came, was strange in a way that still takes some careful thought to fully absorb. Not strange in a frightening way. Strange in the way that the best results in physics are strange. The way a discovery feels when you learn that something you thought was a metaphor turned out to be literal, that a sentence you thought was poetry turned out to be a description. The question was whether supersolidity required matter. The answer, published in Nature in March 2025, was no, or rather, not exactly no, because the answer is subtler than that, and the subtlety is the interesting part. The answer is, it requires something that is matter and light at the same time, in precise quantum mechanical proportions, and that hybrid thing can form a supersolid without any of the nanokelvin refrigeration that atomic systems demand. To understand how, you need to understand what a polariton is, and to understand that, it helps to think first about what a semiconductor does, because the 2025 experiment happened in a semiconductor. A chip of gallium-arsenide, the same class of material used in laser diodes and solar cells and certain kinds of transistors. And the physics happened in the semiconductor's interior, in the quantum states of electrons and their absences. In a semiconductor, the electrons that carry current are not completely free and they are not completely bound. They exist in energy bands, ranges of allowed energies separated by forbidden gaps. At the very lowest temperatures, the electrons fill up the lower band, called the valence band, and leave the upper band, called the conduction band, empty. This is the insulating state, the resting state, when no energy is being supplied and nothing interesting is happening. But when a photon of the right energy arrives, when light of the right frequency hits the semiconductor, it can be absorbed. The photon promotes an electron from the valence band up across the gap into the conduction band. The electron is now mobile. It can move through the crystal, carrying charge. And it has left behind a hole, an absence, a missing electron in the valence band. The hole, counterintuitively, also behaves as a mobile particle. It moves through the crystal as electrons from neighboring sites hop in to fill it, leaving new holes, the absence propagating like a bubble rising through a liquid. This electron-hole pair, attracted to each other by the electrostatic force between the negative charge of the electron and the positive charge of the hole, can bind together into a hydrogen-like composite particle called an exciton. An exciton is a neutral particle. The charges cancel. But it is a bound state, the electron and the hole orbiting their common center like a tiny atom inside the crystal. Excitons can move through the semiconductor, carrying energy without carrying net charge, and they can recombine. When an electron drops back into the hole, they annihilate each other, releasing the stored energy as a photon. Now imagine taking a thin slice of semiconductor, a quantum well, a layer perhaps 10 nanometers thick, sandwiched between two other semiconductor layers that confine the excitons within it, and placing it between two mirrors. Not ordinary mirrors, but semiconductor mirrors of extraordinary reflectivity, grown atom by atom in the laboratory so that they reflect more than 99% of the light that hits them, and they do this at a very specific wavelength. The photon emitted when an exciton recombines cannot escape the cavity. It bounces between the mirrors, reflecting back and forth, and if the photon happens to come back and hit the quantum well at just the right moment, it can be absorbed again, recreating the exciton. And the photon emitted by that exciton recombination bounces again and is absorbed again, and so on. When this cycle of absorption and re-emission happens fast enough, faster than the rate at which either the photon leaks out of the cavity or the exciton loses its coherence, something new happens. The photon and the exciton stop being separate entities that take turns existing. They become, in a precise quantum mechanical sense, a single entity that is part photon and part exciton at the same time. This is not a metaphor. This is a quantum superposition at the level of the material's elementary excitations. The new object, half light, half electronic excitation, is the exciton polariton. Polaritons inherit properties from both parents. From the exciton side, they inherit the ability to interact with each other, to push and pull their neighbors, because the electron-hole pair at their core has charge and extension and a complex quantum structure that two polaritons sharing the same space must negotiate. From the photon side, they inherit lightness, an extremely small effective mass, far smaller than any atom, smaller even than an electron by several orders of magnitude. And this lightness has a profound consequence. The temperature at which Bose-Einstein condensation can occur, the temperature at which quantum statistics take over and particles pile into the same state, depends inversely on the mass of the particles. Heavier particles need to be cooled further before they condense. Lighter particles condense at higher temperatures. Polaritons, with their photon-derived lightness, can condense at temperatures far above what any atomic BEC requires. In some semiconductor platforms, polariton condensation has been observed at temperatures of a few Kelvin. In others, it has been pushed toward and even past room temperature. The nanokelvin refrigerators of the atomic supersolid experiments are simply not needed. This is by itself extraordinary. It means that a Bose-Einstein condensate, the quantum collective state that underlies superfluidity and supersolidity in these systems, can be achieved on a semiconductor chip at temperatures accessible to ordinary cryostats without the years of laser cooling infrastructure that atomic BEC experiments require. But condensation alone is only the superfluid half. For a supersolid, you need the crystal too. You need the periodic density modulation, the spontaneous breaking of translational symmetry, coexisting with the superfluid coherence of the condensate. That is the problem the group at CNR Nanotech in Lecce, Italy, solved in 2025. The team centered on Daniele Sanvito's group, working with colleagues in Pisa and with theorists including Jacopo Carusotto and Dimitrios Tripogiorgos, built a gallium-arsenide microcavity, a chip of semiconductor sandwiched between those extraordinary mirrors. But with a crucial addition, the cavity was not uniform, it was patterned. It was fabricated with a one-dimensional ridge, a corrugated structure etched into the semiconductor at the nanometer scale that imposed a periodic potential on the polaritons living inside it. This is not quite the same as saying the crystal was imposed from outside. The potential was there, yes, but what the Lecce group found was that the polaritons, driven by a laser and interacting through their exciton component, condensed and spontaneously organized themselves into a periodic density pattern within that potential. The condensate developed crystalline order. It broke translational symmetry. It arranged itself into a spatial pattern of denser and less dense regions, and simultaneously it retained the phase coherence of a condensate. The periodic density modulation, see the crystal, and the coherent superfluid fraction existed together in the same material at the same moment. The dual criterion was satisfied. The polariton system, this half-light, half-matter quasiparticle living on a semiconductor chip driven by a laser existing in a regime of temperature that does not require a nanokelvin refrigerator, had achieved supersolidity. The result was published in Nature in March 2025, and it was described as the first supersolid made of light. That framing, a supersolid of light, is evocative, and it is not wrong, but it is worth being precise about what it means. Bare photons, photons in free space, did not crystallize. Photons in free space do not interact with each other and cannot form a condensate. What crystallized was the polariton, the hybrid object, the quantum superposition of photon and exciton. The light and the matter were inextricably mixed, and it was the mixture, with its photon-derived lightness and its exciton-derived interactions, that organized itself into the supersolid state. When people say this experiment froze light into a solid, the honest version of what they mean is, this experiment created a quantum mechanical hybrid of light and matter that self-organized into a state with both crystalline order and superfluid coherence on a semiconductor chip at temperatures far above what atomic supersolids require. That distinction matters, but it should not diminish the strangeness, because the strangeness is genuinely there. The thing that makes this result a landmark is precisely the substrate. Every supersolid that came before, the 2017 BEC supersolids, the 2019 dipolar droplet arrays in dysprosium and erbium, required ultra-cold matter, temperatures within nanokelvin of absolute zero, elaborate and expensive cooling apparatus, atom traps of extraordinary precision. The polariton platform is something completely different, a driven dissipative system, meaning it is constantly being fed energy by the laser that pumps it and constantly losing energy as photons leak from the cavity, but it reaches a steady state where condensation and crystallization coexist. It lives not in the deep quiet of a near absolute zero magnetic trap, but in the continuous flow of energy through a semiconductor chip. It is, in its physical character, closer to a laser than to a Bose-Einstein condensate experiment, even though it produces something that is, by every rigorous definition, a supersolid. And this opens something. The dipolar supersolid in Innsbruck or Stuttgart is beautiful and precisely characterized and enormously important as physics, but it is not, in any practical sense, accessible. It requires equipment and expertise that exists in perhaps a dozen laboratories in the world. The polariton platform is not easy. Growing a gallium-arsenide microcavity with the right patterning requires real semiconductor fabrication expertise, but it is compatible with the infrastructure of optics and photonics, with the tools of semiconductor physics, with the platforms that the technology industry has spent decades learning to make and manipulate. It suggests at the very least that supersolidity need not remain a phenomenon locked in the deepest cold of the most specialized laboratories. It might be studied and eventually engineered in settings far more accessible than a nano-Kelvin magnetic trap. None of this means the polariton supersolid is ready to be used. The 2025 result is a fundamental discovery, a proof of concept, a demonstration that the polariton platform can host the dual order of the supersolid state. The distance between a laboratory demonstration and a practical application is, in condensed matter physics, typically measured in decades. But the proof of concept matters enormously because it says something about the landscape of possibilities. Supersolidity is not confined to one substrate, not confined to one mechanism, not confined to one extreme of temperature. It is, in some sense, a more general property of quantum matter than anyone suspected when Andreev and Lifshitz wrote their 1969 paper. And there is the timeline. When you lay it out, a prediction made in 1969, the experimental hunt begins in earnest in the early 2000s. A celebrated result in 2004, the Penn State torsional oscillator, the apparent NCRI signal in solid helium-4, that seemed for a moment to confirm everything, and that dissolved under scrutiny by 2012. The field's pivot to ultra-cold atomic gases, the patient accumulation of experimental capability through the late 1990s and 2000s, the first BEC supersolids in 2017, the first robust intrinsic supersolid in 2019, confirmed by the secret handshake of two simultaneous sound modes. And then, in 2025, the strangest confirmation of all, supersolidity found in light itself, in the lightest, most massless, most wave-like thing we know, on a semiconductor chip at temperatures the 1969 theorists would never have imagined as relevant to condensed matter. 56 years from the prediction to the photonic supersolid. That is the length of a working life. That is long enough for the graduate students of 1969 to retire before the strangest version of the thing they predicted was finally demonstrated. That is the pace of science when the question is genuinely hard. Not the pace of a mistake or a failure, but the pace of a field following a true question through all the wrong answers and partial answers and unexpected turns until it arrives somewhere nobody originally planned to go. And that brings us to where the story was always heading, to the result that in some ways makes everything before it strange again. Strange in a new direction. Strange in the way that genuine scientific surprises are strange, which is quietly, without fanfare, arriving in a journal paper and only revealing its strangeness the longer you sit with it. It happened in a small city on the heel of Italy's boot, Lecce, a place of Baroque stone buildings and afternoon light, and the kind of unhurried Mediterranean pace that makes it seem, from the outside, like an unlikely home for a physics result that would rewrite what supersolidity means. And yet, the laboratory was CNR Nanotech, the Italian National Research Council's Institute of Nanotechnology, and the group working there was led by Daniele Sanvito, with theoretical support from Dimitrios Tripogiorgos and Jacopo Carusotto, and collaborators in Pisa and beyond. And what they published in Nature in March 2025 was, on the surface, a quiet thing, a measurement, a set of interference patterns in a semiconductor device, the kind of paper that takes expertise to read and patience to appreciate. But let's take it slowly, because the thing they did deserves to be understood rather than just named. Let's actually look at what happened inside that device, because the mechanism is the point. The mechanism is what makes it remarkable, and if we pass over it with a headline and a wave of the hand, we lose the thing that makes the 2025 result genuinely different from everything that came before. So, light. Photons ordinarily do not interact with each other. You can cross two beams of light, and they pass through each other without so much as a flicker of acknowledgement. Two flashlights aimed at the same point in space. The beams cross, each carrying on as if the other isn't there. No collision, no deflection, no force. This is one of the foundational facts of optics, and it is one of the reasons light seems like such an odd candidate for condensed matter physics. Condensed matter is about interaction and about particles jostling and binding and organizing themselves because of the forces between them. Atoms do this, electrons do this, but photons in open space simply do not. They are the loners of the quantum world. They pass through each other like ghosts, which makes what happens inside a semiconductor microcavity so surprising, because inside the right kind of semiconductor structure, you can, in effect, give photons a social life. You can make them interact, not directly. They still don't push and pull each other bare, but you can engineer a situation in which photons become something else, something part photon, part matter. And that hybrid inherits the best of both. Here is how it works, and I'll take it a step at a time because the mechanism is genuinely beautiful. Imagine a very thin slice of semiconductor, gallium-arsenide, in the 2025 experiment. Gallium-arsenide is a material used in solar cells and laser diodes, a workhorse of photonics. You grow it in very precise layers, a few nanometers thick each, a process called molecular beam epitaxy that deposits material atom by atom, layer by layer, in a way that makes the resulting structure extraordinarily regular. Inside one of these thin layers, called a quantum well, you can trap electrons in two dimensions. They're confined. They can move sideways but not up or down, and when you shine light into the quantum well, a photon can be absorbed and create something called an exciton. An exciton is a bound pair. An electron and a hole, the absence of an electron, which in semiconductor physics behaves like a particle with a positive charge. The photon knocks an electron loose from its home, and the electron and the hole it left behind are attracted to each other, orbiting around their common center of mass like a tiny hydrogen atom made of a particle and its own shadow. This is the exciton. It's part matter. It's an excitation of the semiconductor, a real quantum mechanical object with mass and energy and the ability to move through the crystal lattice. Now, above and below the quantum well, above and below the thin layer where these excitons live, you place two mirrors. Very flat, very precise mirrors made of alternating layers of semiconductor with slightly different compositions, tuned so that they reflect light at exactly the frequency of the exciton. The result is a microcavity, a tiny optical prism. A photon can bounce back and forth between these mirrors, confined, trapped, bouncing many thousands of times before it finally leaks out. And here is where the magic happens. A photon bouncing inside the cavity and an exciton living in the quantum well right in the middle of it. When the photon's frequency matches the exciton's frequency, and when the mirrors are close enough together, these two objects don't stay separate. They mix, they hybridize, they enter a quantum superposition of being a photon and being an exciton simultaneously. Not one, then the other, not averaged together, but genuinely both at once in the way that only quantum mechanics permits. The resulting entity is called an exciton polariton. An exciton polariton is part light, part matter. Say that again slowly: part light, part matter. It has some of the properties of the photon from which it was made, including, crucially, an almost vanishingly small effective mass because the photon part contributes almost no mass at all. But it also inherits properties from the exciton, including the ability to interact with other exciton polaritons because the matter part of one polariton can interact with the matter part of another. These are no longer the ghost-like photons that cross beams without acknowledgement. These are particles that push and pull each other gently through the exciton component they carry. And they are extraordinarily light. Their effective mass can be 10,000 times smaller than an electron's mass. In some platforms, 100,000 times smaller. That extreme lightness matters enormously, because in quantum mechanics, the critical temperature for condensation, the temperature at which a gas of bosons gives up its individual independence and collapses into a shared quantum state, scales with mass. The lighter the particle, the higher the temperature at which this collapse can happen. For rubidium atoms, getting colder than a fraction of a microkelvin was required to reach condensation. For exciton polaritons, the mass is so tiny that condensation can happen at temperatures far, far above absolute zero. In some experimental systems, at or near room temperature. In the Lecce experiment, without the nanokelvin refrigeration that the dipolar atomic supersolids demand, the polariton condensate can form on a semiconductor chip pumped by a laser, sitting in a laboratory without a dilution refrigerator in sight. This is the platform that Sanvito's group worked in. And what they added, what made the difference, was a spatial structure. The gallium-arsenide microcavity in the 2025 experiment was not a plain, featureless mirror sandwich. It had been patterned, shaped, to include a one-dimensional ridge, a lattice. Think of it as a tiny corrugated groove etched into the surface, running in one direction, regular and periodic, like the teeth of a very fine comb. This ridge acts as a periodic potential for the polaritons moving through the cavity, a landscape of gently alternating hills and valleys that nudges the particles along, organizes their allowed energies into bands, gives the system a preferred spatial rhythm. And then the laser comes on. A laser pumps polaritons into this patterned cavity. The polaritons condense. They enter a shared quantum state, like a Bose-Einstein condensate, because their mass is so tiny that even at the operating temperature of the experiment, the thermal energy isn't enough to keep them all independent. And as they condense, they spontaneously arrange themselves into a periodic density pattern. The condensate is not uniform, it has a spatial rhythm. It peaks and dips with a periodicity set by the structure of the cavity and the interactions between the polaritons. A crystal, in the sense that matters, a state of matter with spontaneous long-range spatial order, a regularly repeating arrangement in space. But it's still a condensate. It still has long-range phase coherence, every part of the system locked to the same quantum phase, able to flow without friction. The two properties are present together, the periodic order of a crystal and the phase coherence of a superfluid. That is the dual criterion. That is supersolidity, simultaneous, spontaneous breaking of translational symmetry, which gives the crystal, and of U1 phase symmetry, which gives the superfluid. And in March 2025, for the first time, it was demonstrated in a system whose constituent particles were not atoms or molecules or ions, but exciton polaritons, light matter quasiparticles, a condensate of something that is half photon. The headline said, "Scientists froze light into a supersolid." The truth, and the truth is more interesting, is that they created a state in which light-matter hybrids self-organized into a crystal while remaining a superfluid. The photons were not frozen in the way ice is frozen water. The polariton condensate self-organized. The crystalline structure was not imposed from outside. It arose spontaneously from the interplay between the polaritons' interactions and the cavity's periodic potential and the drive from the laser. This is the same interaction-driven mechanism that underlies the dipolar atomic supersolids of 2019, not the vacancy mechanism that Andreev and Lifshitz imagined in 1969, but the modern picture where competing interactions cause the superfluid to choose to break its own uniformity and settle into a crystalline pattern without ceasing to be a superfluid. The headline was evocative and not wrong in spirit. But the substance is a superfluid crystal of light matter quasi-particles that spontaneously chose to be both things at once, and that is, if anything, stranger and lovelier than the headline. Let's stay with that image for a moment. Settle into it. You are lying somewhere warm. Maybe there's still a lamp on in the room, a low and steady light. And somewhere, right now, in a laboratory in southern Italy, there is a chip of gallium-arsenide no larger than a few millimeters, and on that chip, under a laser beam, a quantum state is forming, or was forming, in March 2025 when the experiment ran. A gas of half-light particles condensing and arranging themselves into a regular pattern, every quantum wave locked in step with every other, while the whole ordered structure retains the ability to flow without the slightest friction. It is, in the most precise sense available to physics, both a crystal and a superfluid, both things at once, not alternating between them, not averaging them, both simultaneously, right now. The coldest atomic supersolids require temperatures in the nanokelvin range, billionths of a degree above absolute zero, a temperature that is, when you think about it, almost implausibly extreme. Absolute zero is 273.15 degrees Celsius, and interstellar space, the vacuum between galaxies, one of the coldest environments that exists naturally, sits at about 2.7 Kelvin, warmed a little by the cosmic microwave background radiation left over from the early universe. The atomic supersolids are colder than that. Engineered cold achieved through lasers and magnetic traps and evaporative cooling, cold that the universe doesn't naturally produce in accessible places. The arrays of dysprosium or erbium droplets that Francesca Foligno's group in Innsbruck and Tilman Pfau's group in Stuttgart and the Pisa researchers assembled in 2019, those exist at temperatures that are genuinely among the coldest matter ever made by human hands. A handful of quantum droplets, each containing perhaps thousands of atoms, arranged in a line like beads on a string, each droplet a superfluid, each maintaining phase coherence with its neighbors. Thinner than air, colder than space, visible only through their interference patterns on a detector. You cannot hold one, you cannot see one with the naked eye, you cannot point at one and say, there it is. They are whispers. The polariton supersolid in Lecce is different. It lives on a chip. It is created by a laser, the same technology that reads the disk in an optical drive, or performs laser eye surgery, or cuts metal in a fabrication facility. The microcavity is a piece of engineered semiconductor, expensive and precise, but made using fabrication techniques that are, broadly speaking, cousins of the techniques that made the processor in the phone beside your bed. It is not cold, not in the nanokelvin sense. It is driven and dissipative, meaning the laser constantly pumps energy in and the polaritons constantly leak out. The photon part of a polariton always has a tendency to escape the cavity, bleeding away as real light. But the system maintains its condensate state as a dynamic, steady state, like a fountain that keeps its shape because water is always flowing through it. This is a genuinely new regime for supersolidity, and it matters for what might come next, not because the 2025 experiment has immediate practical applications. It doesn't, not yet, not in the way that a new battery material or a new drug might. It matters because it demonstrated that supersolidity is accessible on a platform that physicists and engineers already know how to work with. Semiconductor microcavities are not exotic. They are not buried in cryogenic dilution refrigerators accessible to only a handful of specialized laboratories in the world. They are, relatively speaking, buildable, patternable, integrable with other photonic structures. The physics of exciton polaritons has been studied for decades precisely because polariton devices might one day do interesting things with light, ultra-low power switches, light-based computing elements, novel laser sources. The 2025 result doesn't make any of those applications immediate, but it establishes that this system, the polariton condensate in a patterned semiconductor microcavity, can reach the supersolid phase. And that means all the theoretical machinery developed for supersolids, all the predicted behaviors and phenomena and potential uses that come from having a state that is simultaneously crystalline and superfluid, can now be investigated in a setting that is, compared to nanokelvin atomic gases, vastly more accessible. It also means something deeper, something about what supersolidity actually is. When Andreev and Lifshitz wrote their 1969 paper, and when Anthony Leggett followed in 1970, the natural habitat for supersolidity was obvious. Helium-4, the lightest noble gas, the textbook quantum solid. Helium at atmospheric pressure stays liquid all the way down to absolute zero. It never solidifies under its own steam because quantum zero-point motion keeps the atoms jiggling too much for the lattice to lock in. And you need to apply roughly 25 atmospheres of pressure to squeeze it solid. That solid, Andreev and Lifshitz proposed, might host vacancies, missing atoms in the lattice, that could themselves Bose condense and flow while the lattice stayed rigid. The logic was elegant, the substrate was specific. Helium-4 under pressure at the coldest temperatures achievable. That was the picture. That picture, we now know, was not quite how supersolidity actually works. The real supersolids of 2019, the dipolar droplet arrays, are not crystals hosting flowing vacancies in the Andreev-Lifshitz sense. They are superfluids that spontaneously chose to become crystals. The interaction-driven picture is different from the vacancy picture. What happens is that when the competing interactions in a dipolar quantum gas, the short-range repulsion between atoms and the long-range magnetic dipole-dipole attraction, reach a certain balance, the ground state of the superfluid is not a uniform gas, but a modulated one. The system finds it energetically favorable to arrange itself into a periodic pattern, a crystal. But the superfluid coherence, the shared quantum phase, the long-range order in the wave function, persists across the droplets. Each droplet is part of a larger whole. They are separate enough to constitute a crystal and connected enough to constitute a superfluid. And the polariton supersolid of 2025 is also interaction-driven. The periodic cavity potential and the interactions between polaritons conspire to make the condensate choose to be periodic. Not because vacancies are flowing, because the system, given the choice, prefers both broken symmetries at once. This is the modern understanding. Supersolidity is not a property of helium-4 specifically, not a peculiarity of a particular atomic species, but a phase of quantum matter that arises wherever the conditions for simultaneous translational and phase symmetry breaking are met. You can meet those conditions in magnetic atoms, you can meet them in a semiconductor device, you might, in time, meet them in other substrates entirely, substrates nobody has thought to try yet. The 1969 theorists planted a seed in helium-4 and specified a mechanism they believed to be the root. They were right about the destination. Supersolidity is real, the simultaneous breaking of both symmetries does happen, the phase exists, and interestingly wrong about the root. Science does this. The correct prediction and the incorrect mechanism can coexist, and when they do, the eventual experimental resolution is richer than either side imagined. Andreev and Lifshitz and Leggett got the thing right. The field found the thing by a different path, and in 2025 the different path led to light. 56 years. Say that again, gently, the way you would if you were telling a story to someone half asleep. 56 years from the prediction to the photonic supersolid, from 1969 to 2025, from the paper written by Andreev and Lifshitz at a Soviet institution, in a world where the semiconductor microcavity had not yet been invented and gallium-arsenide-based quantum wells were far in the future, to a measurement taken in Lecce, Italy, with equipment that would have seemed miraculous to the authors of that 1969 prediction. The graduate students who read that paper when it was new, who found it exciting, who began thinking about how one might test it, who perhaps spent years working on solid helium-4 before the Penn State result of 2004, seemed to confirm everything and then dissolved. Some of those people would have retired before 2025. Some would not have lived to see it. The timeline of a hard scientific question does not care about careers or lifetimes. The question simply waits. In between 1969 and 2025, there was, of course, the false dawn. Yoon Seong Kim and Moses Chan at Penn State in 2004 found an anomaly in solid helium-4 using a torsional oscillator, a device that measures how much something resists rotation. When they cooled solid helium to very low temperatures, the oscillator appeared to become lighter. The apparent moment of inertia dropped, as if a fraction of the solid had decoupled from the rotation, had stopped turning with the container. This was precisely the signature Leggett had predicted, the non-classical rotational inertia. NCRI, the experimental fingerprint of a supersolid fraction flowing frictionlessly through the surrounding crystal while the crystal itself rotated. It was reported widely, it felt like confirmation. It was treated for several years as the experimental verification of what the theorists had predicted. And then the careful work of disentanglement began. John Beamish and others showed painstakingly that solid helium-4 under these conditions changes its mechanical properties as it cools. Specifically, its shear stiffness, the resistance of the solid to being sheared sideways, increases at low temperature when dislocations in the crystal become pinned. Those dislocations bind to impurities, specifically helium-3 impurities, present even in very pure helium-4 samples. And a stiffer solid in a torsional oscillator experiment looks like a lighter solid. The resonance frequency shifts in a way that mimics the NCRI signature. The anomaly Kim and Chan found was real, but it was a mechanical effect, not a superfluid effect. The solid was stiffening, not flowing. And Moses Chan himself, in refined experiments published in 2012, found that when he was more careful about the helium-3 impurity content, the supersolid signal essentially vanished. Solid helium-4 supersolidity, the thing the 1969 theorists had specifically predicted for this specific substrate, remains unconfirmed. After decades of work, the hunt found nothing in helium. That is not a failure. That is the hunt working correctly. A false positive identified, tested, and corrected. A substrate ruled out, or at least complicated enough that the search moved on. And moving on led somewhere better. The pivot to ultra-cold atomic gases in the mid-2000s was not a sudden decision, but a gradual recognition that the tools available in that field, the extraordinary precision of laser cooling and trapping, the ability to tune interactions between atoms using Feshbach resonances, the diagnostic power of time-of-flight imaging, made it possible to construct and interrogate quantum states in ways that were simply not available in solid helium experiments. Bose-Einstein condensation had been achieved in 1995 by Eric Cornell and Carl Wyman, working with rubidium at Gila in Boulder, Colorado, and independently by Wolfgang Kettel, working with sodium at MIT. Both groups shared the 2001 Nobel Prize. A Beck is already a superfluid. It already has long-range phase coherence and frictionless flow. What it lacks, in its simplest form, is crystalline order. The challenge for making a supersolid from a Beck was adding that spatial periodicity without destroying the coherence. In 2017, two groups found ways to do it. Tillmann-Esslinger's group at ETH Zurich coupled a Beck to two optical cavities, two sets of mirrors that the atoms could interact with, and found that above a certain pump strength, the atoms spontaneously arranged themselves into a density wave pattern, a self-organized crystal, while retaining superfluid coherence. At MIT, Kettel's group used spin-orbit coupling, a technique that entangles the momentum of atoms with their internal spin state, to create a stripe phase in a Beck, a spatially modulated state. Both results appeared in Nature in March 2017. Both were supersolid-like, both were important, and both had aspects that made physicists hesitant to declare complete victory. The cavity-mediated self-organization relied on the specific geometry of the cavities rather than the intrinsic interactions between atoms. The spin-orbit stripes were subtle and the superfluid fraction difficult to isolate cleanly. The cleaner result came in 2019 with a different class of atoms. Dysprosium and erbium are rare earth elements. They are strongly magnetic. Their atoms carry large magnetic dipole moments, meaning each atom is like a tiny bar magnet with a substantial field. In most ultra-cold atomic experiments, the dominant interaction between atoms is a short-range contact interaction, essentially a billiard ball collision. But in gases of dysprosium or erbium, the long-range magnetic dipole-dipole interaction between atoms is strong enough to matter. And this long-range interaction, Lecce, which depends on the relative orientation and distance of the magnetic dipoles, which is attractive in some directions and repulsive in others, turns out to be the ingredient needed to produce, spontaneously, a crystalline structure in a superfluid. When the researchers in Pisa, in Stuttgart under Tilman Bau, and in Innsbruck under Francesca Fellaino cooled their dipolar gases to the nanokelvin range and tuned the ratio of contact to dipolar interactions carefully, the gas did not remain a uniform superfluid. It self-organized into droplets, small, dense, self-bound lumps of condensed atoms arranged in a regular one-dimensional array like beads on an invisible string. Each droplet was a tiny Bose-Einstein condensate, a superfluid, but the droplets were not independent. They shared a single, long-range quantum phase, a common wave function that extended across all of them. The phase coherence, the superfluid property, was a property of the array as a whole, even as the array itself was crystalline. The three groups published their results within weeks of each other in 2019. It was, in retrospect, one of those moments in physics where a question that has been building for 50 years suddenly finds its answer, and finds it simultaneously in three places because the tools and the understanding had ripened together across the community. Each group had been working independently, following the same underlying physics to the same destination. This kind of simultaneous arrival is not coincidence. It is the sign that the field was ready. And the proof? The secret handshake, as we spoke of in the earlier part of this journey. Two sound modes. In an ordinary superfluid, there is one kind of sound, the phonon, the density wave, the ordinary compression that travels through the fluid. In an ordinary crystal, there are phonons too, but they are the sound of the lattice. In a supersolid, because two symmetries are simultaneously broken, there are two distinct modes. One is the crystal mode, the sound of the periodic density pattern oscillating, the droplets in the array moving against each other like a spring system. The other is the superfluid mode, the phase oscillation, the sound of the quantum coherence sloshing, which has no analog in a normal solid. These two modes travel at different speeds, they are distinguishable, and observing them both in the same system at the same time is the smoking gun. It is the experimental proof that you have both broken symmetries present at once, that you genuinely have a supersolid and not just a crystal or just a superfluid. The dipolar groups observed these two modes, reported and confirmed in a series of papers from 2019 through 2021, and that confirmation settled the question. The 2019 dipolar supersolids were the real thing, and then 2025. The March 2025 Nature paper from the team in Lecce and Pisa showed the supersolid signatures in the polariton system, the periodic density modulation, the crystalline order, visible in the spatial pattern of the polariton condensate, regular and repeating. The superfluid phase coherence demonstrated through interference measurements, confirming that the condensate maintained long-range phase order across the pattern, both simultaneously. The dual criterion satisfied in a system whose carrier of quantum coherence was half photon, whose effective mass was many orders of magnitude smaller than any atom, and whose operating conditions required no dilution refrigerator, no nanokelvin cooling, no magnetic trap. This is the leap. Not just that it happened, that it was demonstrated, but what the substrate says about the nature of the phenomenon. Supersolidity, as Andreev and Lifshitz imagined it, was an atomic story. It lived in the physics of atoms arranged in a crystal, atoms moving, vacancies flowing. As the field evolved toward interaction-driven dipolar condensates, it became a story about competing quantum interactions in ultra-cold atomic gases. Both of those framings kept supersolidity inside the physics of matter, of things with mass, of atoms or molecules, of the condensed matter world. The polariton supersolid is a story about light-matter hybrids. It is a story about engineered quasiparticles, about the quantum states that arise when you trap light between mirrors and couple it to semiconductor excitations and let the resulting entity behave as a boson. It is not a story about atoms. The exciton polariton is not an atom. It is not a molecule. It is a dressed state, a particle that exists only because of the particular quantum mechanical environment created by the microcavity. Remove the mirrors and the polariton ceases to exist as a polariton. The photon escapes and the exciton decays. The supersolid state in the Lecce experiment is a creature of the device. It is not found in nature. It does not exist anywhere in the universe except where a human being has built the conditions for it to exist. There is something to sit with there, if you are still awake enough to sit with it. The oldest supersolids in the universe, if there are any, if any naturally occurring quantum system ever reaches a supersolid state, would be atomic, made of matter shaped by gravity and quantum mechanics requiring the right temperature and density and composition. But the newest supersolid, the one confirmed most recently, is a human artifact. It lives on a chip. It is maintained by a laser. It blinks into existence when the power is on and dissolves when the pump is switched off. It is a thing that the universe, left to its own devices, would never make. It exists because people were curious enough and patient enough and skilled enough to build the conditions for it. 56 years of curiosity. 56 years of work. From a theoretical proposal written in 1969, a proposal for a state of matter that should, by all the principles that were known at the time, be impossible, or at least paradoxical, to a measurement taken in a laboratory in southern Italy in 2025 in a device made of a semiconductor material that didn't exist as a laboratory tool when the theoretical proposal was written. That is the length of the journey. That is what following a question faithfully and carefully through all its wrong turns and partial answers looks like from the outside. And at the end of the journey, what do you have? You have a state of matter that is simultaneously solid and superfluid, a crystal that flows. You have it in atomic gases, cooled to within billionths of a degree of absolute zero. And you have it in light, in the lightest, most massless, most wave-like form of quantum matter that physics knows how to make, on a chip at temperatures that any well-equipped optics laboratory could achieve. You have the demonstration that two properties which seem contradictory, rigid periodic order and frictionless flow, are not contradictory at all. They describe different aspects of a system, its spatial arrangement, and its dynamical phase coherence. A system can have both. A system can organize its atoms or its quasiparticles into a regular crystal and still maintain a quantum phase across the whole, and that phase can support flow without any friction whatsoever. The apparent paradox dissolves when you understand what solid actually means and what fluid actually means in the quantum context. Not hard versus soft, not rigid versus yielding, but does the system have long-range spatial order? And does it have long-range phase coherence? Those are independent questions. They can both be answered yes. This is what physics does at its best. It takes a pair of things that seem like they must be in opposition, like the apparent solidity of matter and the wave-like spread of quantum states, and it finds the framework in which they are not in opposition, in which they are simply two different aspects of a system's quantum organization. The apparent paradox was an artifact of a limited framing. The resolution is a deeper understanding of what the terms mean, and the 2025 result adds something to that resolution. It says, this is not just an atomic phenomenon. This is not just something that happens in dysprosium at 5 nanokelvin. It is a phase of quantum matter, accessible in principle wherever the conditions for simultaneous symmetry breaking can be engineered. And those conditions, it now turns out, can be engineered in light matter systems on semiconductor platforms. The universe of possible supersolids is wider than the 1969 theorists knew. Wherever you are right now, and I find myself thinking, as this long night of physics draws toward its close, of all the places you might be listening from, all the corners of the world where someone has found a quiet hour and put on a voice and let themselves drift. Wherever you are made of matter that obeys the same physics. The atoms in your body, the carbon and hydrogen and oxygen and nitrogen, the trace elements, the whole improbable assembly of you, are quantum objects. They obey quantum mechanics. The electrons in those atoms, the ones that make up the chemical bonds and the heat and the light and the motion of you, are fermions, not bosons, which means they follow different rules from the bosonic helium-4 and dysprosium and exciton polaritons we've been speaking of tonight. They cannot, at any temperature, condense into a superfluid in the way we've described, but they are quantum objects nonetheless. They carry quantum numbers. They maintain coherence in certain conditions over distances that would surprise you if you measured them. The same mathematics, the Schrödinger equation, the quantum field theory that underlies all of it, describes both the electron in your nerve cell and the polariton condensate on a chip in Lecce. The supersolid is an extreme case, a laboratory phenomenon, a deliberately engineered state that nature doesn't produce without our help, but it is made of the same physics that makes you up. It lives on the same mathematical substrate. The discovery that light-matter hybrids can form a state that is simultaneously crystalline and superfluid is a discovery about what that mathematics is capable of. A discovery about the range of solutions it admits, the variety of phases that the quantum world can support. And that variety turns out to be richer than anyone in 1969 imagined, richer than the false dawn of 2004 suggested, richer than the 2017 BEC results alone showed. The richness is still being mapped. The 2025 result is not an ending, it is the end of one thread, the long thread of the prediction and the hunt, and the beginning of several new ones. What other platforms can support supersolidity? What does a polariton supersolid do at even higher temperatures? Can the two sound modes be observed in a polariton system the way they were observed in dipolar gases? What other simultaneous symmetry breakings might be achievable in engineered quantum systems? These questions will be answered by people who, in some cases, have not yet begun their physics training. They will be answered in laboratories that don't yet exist, using techniques that haven't been invented. The question will continue. The question, as always, simply waits. But for tonight, the thread we followed has reached its end. A thing predicted in 1969, matter that is simultaneously rigid and frictionless, a crystal that flows, has been confirmed. It was confirmed first in matter cooled to the coldest temperatures humans have ever made in dipolar atomic gases assembled droplet by droplet at nanokelvin temperatures in Pisa and Stuttgart and Innsbruck. And then it was confirmed in light, in the half-light quasiparticles of a polariton condensate on a chip in Lecce, Italy, in March 2025. The prediction took 56 years to reach its strangest demonstration. And the strangest demonstration turned out to involve the most weightless, most wave-like, most unmatter-like thing in the physicist's toolkit, a quasiparticle that is half-photon. That is, I think, a genuinely beautiful thing. Not beautiful in a way that requires you to understand every equation or to hold every detail in your mind. Beautiful in the simpler sense that a long patience was rewarded, that a hard question, followed with honesty through all its wrong answers, eventually led somewhere unexpected and true, that the universe contains more variety than we thought, and that the category we thought we understood, solid, liquid, their apparent incompatibility, turned out to admit a richer resolution than our ordinary experience of ice cubes and flowing water had prepared us for, a crystal that flows. Two things at once, gently. The rigid and the frictionless, holding each other without contradiction, on a chip in southern Italy, in the light of a laser, in a laboratory at the end of a 56-year search. You can let that sit with you as you sleep. You don't need to do anything with it. It will still be true in the morning. The polariton condensate will still have self-organized into its periodic pattern, and Andreev and Lifshitz will still have written their 1969 paper, and the dipolar droplets will still have formed in Pisa and Stuttgart and Innsbruck in 2019, and Moses Chan will still have had the intellectual honesty to let the Penn State result dissolve when the evidence demanded it. All of it will still be there. The physics doesn't change while you sleep. I hope, wherever you are, that the night is a little quieter now, that the long, slow walk through supersolidity, through helium creeping up walls, through torsional oscillators in Penn State, through the nanokelvin mathematics of dysprosium, through polaritons catching light between mirrors and making of it something solid and flowing at once, has left you with a kind of gentle heaviness, the pleasant weight of having learned something real, something that happened, something that took longer than a working life and arrived somewhere nobody originally planned. At the very start of tonight, I asked you to imagine a crystal you could pour through itself, rigid and frictionless at the same instant. I asked you to hold that apparent contradiction and see where it went. I hope, after everything we've covered, the contradiction has softened into something more like a question answered. Not neatly, not in a way that makes it less strange, but in a way that makes the strangeness comprehensible. The solid and the fluid are not opposites. They are not even fully separate categories. They are two different questions about the same system, and a supersolid is what you get when the answer to both is yes. If you've enjoyed this long, slow voyage, and I hope it helped you drift a little, a like and a subscribe mean more than you might think. Small channels like The Curious Voyager rely entirely on the support of listeners like you to keep these journeys going. If you feel moved to leave a like or to subscribe, I'd be genuinely grateful. And if you'd like to leave a comment, tell me where in the world you're listening from tonight and what time it is in your corner of it. I love knowing. I love imagining the range of places and hours and quiet rooms where this voice finds you. To those of you already subscribed, already familiar with these slow evenings, thank you. The fact that you keep returning is the reason this channel exists. And now, the physics will still be here tomorrow. The supersolid will still hold its two impossible properties by morning. The search that began in 1969 has found its strangest answer, and the answer is beautiful, and you have carried it with you through the night. Sleep well, fellow voyager. The next journey keeps until you wake.